Okay. Good morning, good afternoon, good evening. Welcome to this ICRA 2021 workshop on digital twins for rapid design, development and deployment of inspection, maintenance and repair robots in industrial applications. My name is Simon Watson. I'm a senior lecturer in robotic systems at the University of Manchester. My background is in the development of robotic platforms for extreme environments such as nuclear, offshore and subterranean mining. I'm going to be hosting this workshop today. We're going to start with just a few housekeeping and overview sessions, and then we'll jump straight into the very exciting agenda that we've got for today's workshop. If anybody has any questions at any time, please feel free to put them into the chat function and we'll try and answer them as best we can. Housekeeping, as I've just said, the main session activities are going to be recorded. However, when we move into breakout rooms later on, those elements won't be recorded. I'd ask everybody to mute your audio and turn your video off whilst you're in this main room, please. Questions during today's sessions are going to be answered in the two discussion sessions that we have. So this morning you're going to see a number of presentations. If you have questions during those presentations, please put them into the chat room, into the chat function. I will then collate those and keep them for the Q&A session. During the Q&A session, we'll work through any questions that have been raised through the chat. If you would like to ask a question in person, we very much welcome that. Please use the raise hand function and we'll get to you. When we get to you, you can unmute yourself. You can turn your video on if you wish, and you can ask the question. So we'll have a full panel Q&A at the end of the presentations. We'll also have a discussion period as we wrap up as well. So those are several opportunities for us to ask questions. After the first couple of hours, after the presentations and the panel session, we're going to have an interactive mind map development session. I'll explain this in a little bit more detail later on. You'll be invited to join specific breakout rooms covering topics that we'll outline. You're free to jump between these breakout rooms as you see fit. So the discussions will go on for about half an hour where we'll discuss various different topics. If you'd like to swap, we can maximize the flexibility of this virtual format in a way that we may not have been able to do so in an in-person one. I've talked about potential flexibility of this virtual format, and we're very lucky to have speakers from the States, from Europe and from Asia as well. The time zone differences are very challenging, and I thank all of the speakers in advance for being able to participate in this, and you as attendees, because I realise that this is a global session, and so the time zones are probably quite awkward for several of you. We know that virtual events, the networking is more challenging. You know, whilst we'll have a coffee break, you have a lot of conversations with the person stood in the queue for the coffee. We don't have that. So what we're going to try and do is set up some breakout rooms. But to start with, I'd just like everybody to, or I'd like to request that everybody updates their Zoom name so that we can facilitate a little bit of networking. So if I could ask everyone to change their Zoom name so it's their name, their affiliation and their country, I think that will be a great help to everybody. So for example, you can see my Zoom name has my name, where I'm from, the University of Manchester, and which country I'm residing in. So you can do this if you go in the participants panel, you can click on your name and select more and rename, and you can change your name. So if you would be able to do that, that would be very much appreciated, and just maybe help people identify others who they might want to talk to. During the coffee session, we're going to set up some generic breakout rooms where everybody can move to if they wish. This is no substitute to the real networking that you would have in that coffee queue or just stood around waiting at the entrance. But we'll do our best. So if you'd like to chat to somebody, if you see somebody that you've not seen in a while and you want to have a quick chat, please feel free to use that time during the coffee break. We will close the breakout rooms at the end of the coffee break so that we pull everybody back. Just a warning that these breakout rooms aren't private. The way that they're opened and set up to be flexible is that people can come and go as they wish. Okay, so if you want a more private meeting, you may have to arrange that offline. The breakout rooms are not going to be recorded. Okay, so it's only this main room that will be recorded today. In terms of workshop outputs, we're going to be recording this workshop. We'll be placing that on the website. We're also going to be putting the mind map up onto the website as well. We've submitted a proposal to the journal Frontiers in Robotics and AI for a special issue on digital twins for IMR Robots. That's going to be under review over the next week or so. If it's approved, we'll circulate a call for papers, and we would welcome contributions from all of the participants here into this really exciting, new and evolving and emerging area. So please keep your eye open for that call for papers. So today's agenda, before we kind of move on, so we'll finish off the welcome. I'll just wrap this up very quickly. We've then got some excellent presentations. We will have Professor David Lane, Dr. Sungwoon Ju and Dr. Joaquin Carrasco, Professor Manuel Giuliani, Professor Young-Soo Park. There will be a coffee break for 20 minutes, and then we'll have our final presentation from Professor Luca Carlone. And then there'll be the panel Q&A session. We'll have the breakout mind map generation session, then a discussion and wrap up, and then we'll be finished. And we will do our best to keep to the 4-hour time slot today, because I appreciate everybody is very busy and will have other activities to go to. So before we kind of pass on to the presentation, just a bit of an advanced view of the mind map. So we've got an online collaboration tool, Coggle Mind Map, and we're going to be developing a mind map to understand where are we now, where do we want to go to in the future, and what are the major challenges that we need to overcome to realize this vision that's going to be explored during these first set of presentations. There'll be 3 primary areas that we'll be looking at. We've got physical twins, digital twins, and the digital connective tissue. So we'll have breakout rooms in each of those. You may have a particular interest in one of those areas. So, this kind of an advanced warning as to what those areas are, and maybe you can think of some of the challenges that we need to address and overcome in these areas. Okay, I'm going to stop my sharing there, and we're going to move on to our first presenter. So I'd like to introduce Professor David Lane, formerly of Heriot-Watt University, who is going to kick off our presentations. David, if I pass over to you.
Simon, hello, thank you. How are we doing?
We can hear you and we can see you. Yeah.
Perfect. Okay, so hello everybody. Good morning, good evening, good afternoon, good night, wherever you are. And thank you for being here. My name's David Lane. And what I wanted to do with this slot that we have here at the beginning, which Simon kindly asked me to do, is just talk a little bit about where we're going with digital twins in the UK. So I'm wearing my UK Robotics Growth Partnership hat, which is a leadership group which supports the UK government. But really what it's doing is talking about some of the things that have been gestating for the longest time with all these organizations on the left on the slide, which are people have either started or organizations have either started or worked with over the years. I recently had the opportunity to clear out my office after a long time. And 2 of the things I found in my office were posters from when I did my PhD back in 1981. And I looked at them and it was all autonomous underwater vehicles. But I looked at it and I thought, actually, what we were doing at the time was digital twins, as I'm going to describe in a minute. So a lot of the concepts that we're thinking about have been around for a long time. We just haven't called them digital twins. And I have to say, we were trying to run things in those days. Some of you may remember on a PDP 1144, I think we had 64K of memory, if memory serves me well. So, you know, this has been around for a long time. I don't propose to linger on this, but just to say, you know, it's not new. What do I think of as a digital twin? Well, obviously, there's the physical entity and there's the digital entity and data passes between them. The key thing that distinguishes, for me, a digital twin from a synthetic environment is one where there is this interchange of data. So the digital twin is running in real time alongside the physical twin. And as a result of that data sharing, it means that you're able to do all sorts of optimizations across the two entities. And not everybody recognizes that. As I go around government, or indeed as I go around research labs, some people don't realize that. They have the view that a digital twin is just having a synthetic copy. But in reality, having that real-time operation is essential. And the other thing that, this is a very poor quality slide, I apologize, but the essence of it is there, I hope. It's not just about physics and geometry, what goes into a digital twin. The copy is also, so therefore the asset. It's also about the processes and the things that people do with digital twins. So if you like, it's the use cases, it's the workflows, it's the robotic process automation, if you like, if you come from that world. And so it's a much more complex thing. It doesn't just involve the physical asset itself and its copy. It also involves how people use it. And you know, in the blue here, there's a bunch of reasons why these are important. But what I quite like to do is just draw your attention to the red at the top, and it's in red. And just, you know, we're all of us to varying degrees coming out of the pandemic of COVID-19 at the moment. And it's an example of an unexpected exogenous shock to which we had to respond. It's not the only kind of exogenous shock. There are many other kinds that are likely to hit us that we don't know what they are, from sun flares to volcanic eruptions producing global cooling, and the list goes on. And we can't predict what these shocks are going to be. And what we do know, and what we have learned, I think, or had reinforced over the last 12 months or so, is that the countries that have been the most successful at dealing with these have demonstrated agility, some element of paranoia about what to do, and certainly devolved authority to organizations who had tools they could use to innovate at pace. So in other words, to deal with these exogenous shocks, of which we can expect many more in the future. The pre-prepared plans that sit in PowerPoint slides and massive reports that tell us what to do in response to a particular eventuality probably won't help us very much, because the shock that happens isn't the one that you expect. It might not be global warming. That's the thing that gives us the big issue. So digital twins, for me, are essential tools to help us innovate at pace. And I hope to show examples of that, but also ways that we can be better at using them as we go forward. So there's a lot of things in here. I'm not going to go through them now. You can have a look at them afterwards on the movie about how we do it. Perhaps I can do it better by illustrating some examples in a minute. One of the things that I think has really struck me about how I and others have certainly innovated in the past using digital twins, it goes something like this through various phases where, we kick off with doing some simulation because we don't know how big or how long or how fast, how much energy, whatever the parameters are. And then we go to a stage where we start to do sort of hardware in the loop emulation. We're maybe running some flight code, but we've got some simulations running with it because we're still not sure about how it all comes together. And eventually we build sort of MVPs, first prototypes that sit in living labs. So these are environments where people can interact with, in this case, robots, smart machines. And we de-risk in a safe environment, particularly where it involves operating with people. And then eventually we get out to some kind of site lab, I've called it. So we get out into the real world and let them run loose. And so, you know, the technology readiness level of what we're doing increases as we go up here. And the sort of underpinning technology that allows us to do this and go through these phases is digital twins, not only to do this, go up this hierarchy, but also to visualize what's going on. I'd like to just give you some examples from my career of examples of where we've done this kind of thing. This is the thing called the autonomous inspection vehicle. I think I saw Jim Jameson from Subsea 7 on here earlier on, so hello Jim if you're there. This was a great collaboration between a company called Seabite, came out of the Ocean Systems Lab at Herrick Watt, and Subsea 7, if you don't know, they're one of the world's largest tier 1 contractors in the offshore energy industry. And this was a piece of work now, it's 10, coming 15 years old, but it was developing an underwater vehicle, autonomous underwater vehicle that can do deep water inspection around floating production systems. And this isn't a research prototype, this is a commercial piece of kit. It does real work in the Gulf of Mexico and indeed in the North Sea. We wouldn't have been able to develop this had we not had that pipeline of activity. And in particular, things like getting the visual surveying from sonar to work. It uses sonar to localize itself relative to the subsea assets. You know, there's no way we would have got this working without that pipeline of activity, because once you get offshore, it has to pretty much work, otherwise it's too expensive. Some of the other kinds of things that we've played around with, building on that idea of autonomous vehicles in the ocean. It wasn't called planetary digital twin at the time, but it's becoming that now. In the early days, some of you may know Jim Bellingham, people like that, who are formerly from Monterey Bay Aquarium Research Institute, latterly of Woods Hole, adaptive oceanographic sampling networks. The basic idea is that you want to make estimates at scale at different resolutions in space and time in a water column of oceanographic parameters, so conductivity, depth, salinity, those kind of things. You can't measure that in those sort of volumes. So the way you do it is by running models of that, simulations if you like, but you run them in lockstep with real platforms, vehicles, vessels, planes that are making measurements, point measurements generally over a short period of time. And then you do a kind of Kalman filter thing called data assimilation by the community. But the idea is that you can then use the model to use the real measurements to anchor the model to get an estimate. And this is a very powerful way of measuring these parameters. And as we'll see later on, if you start to think about how can I connect these models, then the prospect of a planetary digital twin, where we're running measurements on the planet with simulations and models of different atmospheric effects, environmental effects, becomes feasible. And I'll come back to this point about federating twins later on. This is an example from a thing called the Orca Hub. I think we might be hearing some more about this. There's a series of hazardous environment activities being funded in the UK through the Industrial Strategy Challenge Fund. And here what we're doing is looking at robotic systems that we can use on offshore energy infrastructure for inspection, repair and maintenance. And this is the work of Dr. Alex Lee at the University of Edinburgh. Okay, the animal quadruped's falling over, but the way that we learn about how to get it to stand up in this situation is not by working with the real robot, by work with simulation. So we can use digital twins to help us to do machine learning with the asset to make sure we know robot, see how it works. This is the work of Professor Sethi Vijaykumar, University of Edinburgh, and some of his team. Many of us will be doing similar things to this, where we're running a variety of sensors to do mapping. This is an example of shared autonomy, where he's varying the level of autonomy from full autonomy to teleoperation, depending on the phase of the activity that's going on. But this is the kind of activity that generates certainly the physical property, the physicality of the digital twin. One of the good things about having this is that you can then start to interact with it in unusual ways. And here I'm illustrating the work of Professor Helen Hastie in the Edinburgh Centre for Robotics and her team, again part of the Orca Hub, with a thing called Miriam, which is a personal assistant. And if you think about WhatsApp or WeChat, depending where you are, running with your robot, interrogating your digital twin. You'll see in the main window there's a conversation going on, and there's a variety of robots being used to do, in this case, there's a fire and there's the response to the fire, and there's some mapping, and then there'll be some intervention. And you can interrogate the system. So you can ask the system what's happening, why are you doing this, and get that explainable AI, that trust between operator and system through the digital twin, which has generated the data using the robots earlier on. So these are some of the sort of powerful things that you can do. And many of you may have heard of the British company Ocado. People think, most people probably know them, except in this community perhaps. Most people know them as a grocery company. They do online delivery of groceries. They don't have any shops, but they do have warehouses. And this is one of the Ocado warehouses in the UK, where they're using robots in order to effectively sort your order into the package that you eventually get. And none of this would have been possible without the use of digital twins. And my colleague Paul Clark, formerly CTO of Ocado, was responsible for developing this, and my co-chair of the UK Robotics Growth Partnership. And again, this warehouse design is now being cookie cut all around the world. The US, South America, Europe, the ones I know about, and there's probably many more as well, as an example of British technology being exported. And then finally, in my examples, I want to mention Miro Cloud. This is Miro. There's a couple of them back there in the image if you're looking. It's a social robot. This is a chap at I think this might even have been an ICRA conference. I'm not sure. You may have seen a Miro at conferences before. So it's all about interaction. It's multi-sensor, but we use a digital twin of Miro in a thing called Miro Cloud, actually for teaching programming to kids from age 8 all the way up through senior school, secondary school, K-12, again, depending where you are, and actually on into university in Python, as well as in a thing called, I forgot the word, Blockly, sorry, on the left there, which is great for kids when they're starting to learn. So lots of applications of digital twins, and you can program in the digital twin and then download to the real robot. So you can do it from anywhere through a browser and through a screen. So examples of the power of what you can do with a digital twin. The real thing I want to sort of kind of end up on today is talking about not just what's the potential of a digital twin as we use them at the moment, but what happens, what's the future of digital twins? How are we going to develop them? And the theme I want to develop is around federation. Here's an example of digital twins that we can federate. We haven't done it yet, but it's on the list of things to do. Digital twin of the engine of the aircraft, top left, works with a digital twin of the aircraft, works with a digital twin of the airport, works with a digital twin of the baggage handling system, works with a digital twin of the people that are coming in and out and getting on the airplane and so on. If we can connect these digital twins, federate them in an easily and seamless way, then it becomes a very powerful tool for doing a lot more than you would normally do with a single digital twin, such as the examples that I've just shown. So in the UK, we've been working towards, with the UK government, and the Robotics Growth Partnership has been part of this, but also the AI Council and a number of other bodies, to develop this notion of what we call the cyber physical fabric, which is effectively the software glue that allows us to connect digital twins. And I've deliberately, many of you might recognize this picture from Iron Man, the Iron Man movie, and Jarvis. This is the beginning of the idea. It's 10 years old now, more than that perhaps. But it's turning this kind of idea into some kind of reality.
Our material economy is built on combining experience, intelligence, and physical action. Over the last 100 years, we have made machines work better for us. In the beginning, these machines worked in isolation, processing for information. Communication has now connected them together. The next step is cyber-physical services that connect data and knowledge with physical action. These cyber-physical services are built on digital twins that capture real-time data, human experience, use AI to manage complexity, and robots to deliver physical interactions. Together, they weave a cyber-physical fabric that interacts with us and the world around us, and does so with knowledge. We have the threads, but haven't yet made it easy to weave them together. By building and sharing digital and physical resources, we can create the cyber-physical fabric that makes it easy for everyone to build connected smart machines. The fabric is a connected ecosystem for innovation and collaboration. It enables anyone to go from the idea of a cyber-physical service to virtual testing before trying the solution in a physical test bed and a living lab. The fabric is a new material from which we can fashion all manner of new products and services.
Cool. So, cyber physical fabric. I don't have enough time to really go through it. Here's a diagram. Broadly speaking, at the bottom, the three things at the bottom, we call it the cyber physical web, where it's the glue, the software glue, the standards, we call it digital commons, the common software that used by everybody, owned by nobody, rather like the web and the internet before it, that allows us to connect these together. The components, the way we use AI, shared synthetic environments, digital twins, connected smart machines. And from that, effectively, this is the tools that I talked about at the beginning. If we can realize this, then it gives us the tools that everybody uses every day through their desktop, through their browser, in order to develop systems, smart systems, in a way that can be agile and can be responsive to and give us the resilience that we seek, and also the productivity and prosperity that we seek also in our nation states. So again, I don't have time to really go through this. I would highlight, some of us are starting to understand NFTs, non-fungible tokens, and the way that with Bitcoin and these new cryptocurrencies, actually the penny that dropped in my head, penny is a British word, sorry, it should be cent or yen or whatever, yuan or whatever, that dropped in my head recently was that the way crypto is going is exactly the same way we're going in robotics with this cyber physical approach. And so when you start to want to represent the value of the asset you're working with and be able to trade it, that suddenly becomes something that you can integrate into this cyber physical web. Don't ask me how yet, we haven't done it. And it's all evolving, but you can see the sort of power and the direction of travel of this thing that we're doing. So thank you very much, everybody. I'm just on time to finish. I look forward to any questions you might have, and indeed to cooperating and interacting with any of you who might have an interest in this kind of thing. Although we're thinking about it here in the UK as something we want to do for our own sort of national prosperity and resilience, all those things we talked about. Actually, it's an international project. It only works if everybody gets on board and gets interested in it, in the same way that the internet and the web were like that as well before it. So, we welcome dialogue with anybody that has an interest in this area. Thank you very much.
Thank you very much, David. Really, really interesting talk, especially the bit at the end about how, the parallels to the cryptocurrency and NFTs and how that might kind of almost, can you observe the mistakes that are being made in that? What are the pitfalls and how can you learn lessons? I think that's really, really interesting. And I'm sure it'll be a topic of discussion in the panel Q&A session at the end. So thank you very much. We're going to move on now and have our next presentation. So I'd like to welcome Dr. Sungmoon Ju and Dr. Joaquin Carrasco, and I will hand over to you now.
Thank you, Simon. I will start the presentation.
That's good. We can see that.
Good. Perfect. Thank you. So this presentation is a summary of the work that we are doing between three different partners: the University of Manchester, RACE, Robotics Application in Challenging Environment, and CARI, the Korean Atomic Energy Research Institute. The project here is the digital twin-based bilateral teleoperation system for nuclear applications. I am Joaquin Carrasco, and Sungmoon is also here with me, that will be presenting the second part of the presentation. This project have been funded by the two different, the UK funder and the Korean funder, the EPSRC in the UK and then NRF in Korea. So what we are trying to do here, so in this presentation, sorry, we are going to try to provide a short introduction to the project. After this, we will give you a short summary of the technical progress that we are doing during the last year, and finally we will also present the future work in the last year of the project that we are planning to do. So the team RACE have a huge expertise in bilateral teleoperation. They have been maintaining JET, the European kind of project in fusion energy for the last 30 years. In RACE, Salvador, IPEC, and Rob are the team members, and they are mainly based on they are working in the point cloud compression and the completion of the point cloud, and how to send this information between master and slave. Here in Manchester, Hanlin, Huyen, and myself, we are working in the area of the bilateral teleoperation, so trying to produce the master site, trying to understand what is the effect of the delay, and Huyen is also helping us in the machine learning techniques that we are using in this project. At Kerry, sorry, yes. At Kerry, Huyen is and Simon are working in the part related with the understanding of what is in the slave side, and Simon will provide more details later about their part of the project. So the big picture of the project is in this slide. So basically, we are trying to develop a digital twin of the real world in the master site. So this part, this part here is what we are trying to implement in the master site, where we are building, as David had been previously commenting, we are trying to not only put in there a digital twin, but also evidently understanding how the real world is behaving, and then putting a simulation where actually we can understand if we are touching the first time an object, maybe we don't have a very good understanding of what is the force that this object is going to do over the gripper, but as we are picking up the same object, we will understand what is the mass of the object, we will understand how it's going to move. So as it is not only just putting there the system, but evidently we need to be understanding using machine learning techniques to understand the environment in a better way. Also, we will be able to maybe to put radiation sensors and then understand what is the safer operation path for the robot. So it is a continuous development of in closed loop of what is happening in the environment. The aim why we are trying to put this there is to save the problem of the communication, or evidently the communication will be introducing a time delay. And if we are doing haptic teleoperation, or if we are doing bilateral teleoperation, it's always difficult. In addition, maybe if we are doing serve control, we are also able to if we are doing serve control, we are also able to actually to understand if the robot is behaving in the way that we can run a simulation checking that the robot is behaving in the way that we want the robot to behave. In Manchester, we have been developing, actually the last summer, we have a cross-hub activities. And then what we have been trying to develop is a very simple virtual reality environment that the user can see. So we have a test with the University of Edinburgh. Basically, the connection was done through the internet using Amazon Web Servers. Then through a VPN, we were able to use the EduRAM connection between both universities. In Edinburgh, they have a virtual reality headset with just a lip motion sensor to measure the position of the hand. And then in Manchester, we have a Universal Robot 5, just to. So this picture here, so this will be the slave side. Then, sorry. If I am able to go back, let's see if this works. Thank you. This part here, it is the virtual environment. And finally, the operator was able to develop this task in just 15 minutes, showing that it was a very easy to use kind of virtual environment. As you can see, I don't know if it's clear, but basically here we were using a 2D image of the environment. So what we are trying to do in the project is now using a point cloud compression and decompression system. So in the environment, so here we have the slave, here we have the master. So we are trying to generate a combination between virtual reality, so between the CAD model that we already have of the robot, and then with the environment. And in the environment, maybe we have the CAD system, the CAD model of something that is in the environment, or maybe we have something that is new and we need to identify. So we have been trying to do segmentation techniques to understand what is the best way of sending information, of splitting this point cloud and sending more details of the object of interest, and then maybe less details of the object that we know that are going to be there. We already have a model of the table, and then therefore we don't need to send this information. So we are trying to improve the speed of the communication between master and slave. Something interesting in this kind of scheme is that we will have like a combination between point cloud or part of the point cloud of something that we already have. So for example, in the robot, you can see here how there is you can see the label of the point cloud that is coming from the slave. And then we are trying to remove all this information that you don't need to improve the speed in the communication between master and slave. This ends my part of the presentation. The second part of the presentation, someone is going to be explaining how they are actually recognizing what is in the point cloud and what techniques they have been using to understand what is in the slave. Someone?
Okay, I'll be taking over. Sorry, do you see my presentation?
Yes.
Okay. Hello, everyone. Thank you, Joaquin, for a nice introduction of our collaborative projects and describing the UK portion in the project. So as Joaquin mentioned earlier, in Korea, we've been trying to develop some technologies that can help in the creation of 3D digital environments from 3D scan data. And basically what we want to do is develop a system that takes a point cloud as an input and generate a 3D model of the environment. So, okay, over the last 2 years, we've been developing 3 technologies. The first one is developing a robotic scanning system for automatic 3D scanning. So basically what we developed was a scanner attached to the end effector position of a robotic arm, and the operator can control the position and orientation.
Slider bit missing.
Hello? Sorry?
You can go.
Okay, so the operator can control the position and orientation of the scanner using either a haptic device or a keyboard interface or a GUI interface. And after we got sufficiently enough scans from the environment, we can register those scans into the whole point cloud. And once we have a point cloud of a target objects, we need to identify what those scan means. So instead of using traditional machine learning method, we adopted a deep learning approach, which means we need a lot of training data because we have very limited access to actual power plants. What we did was use a CAD model and simulate the scanning process using a open source software called Glancer. And what you see on the top right here is a snapshot of simulation. And the orange color means the point cloud, simulated point cloud of the reactor internal structure. And from the CAD model, we cut those CAD model into 22 parts like this. And then using the simulated data, we trained a deep learning model. The deep learning model, classification model, takes a point cloud as an input, and it computes scores or probability of that point cloud. And then we choose the category that has the highest score or the probability. And using the simulated data, we train the model. And in the train, our performance metric is at accuracy. And in the training phase, we got like over 95% of accuracy. And we validate our model using actual real scan data. And because we 3D printed some of the parts and get the real scan data. And in the validation, we got over 90% of accuracy. And I think it's pretty good. And the next step was to develop a segmentation system. And out of 22 categories, we pick 7 categories that can be divided into subparts. For example, here in closure head assembly model, this model can be divided into 5 subparts like this. And for those 7 categories, we annotated the scan data with the help of very highly motivated undergraduate interns. And after we got these annotated data sets, we trained our deep learning model using the data. And this segmentation model takes a point cloud as an input, and it computes per point classification score. And for each point in the point cloud, we have to solve this classification problem. And those color means different subcategories this deep learning model estimates. And in the training phase, using this simulated annotated data set, we got our performance metric is intersection over union, which is pretty common performance metric for segmentation job. And we got over like 0.9 is our work performance. And we validate our model using actual real scan data, and we got very similar results from the validation. So I guess this is the last slide. So with the aim of developing digital twin-based bilateral teleoperation system for nuclear applications, UK and Korea has been collaborating over the last 2 years. And in UK side, they've been developing intuitive VR teleoperation architecture and efficient transmission point cloud method. And in the last year, which is this year, they will focus on the development of reinforcement learning algorithm for teleoperation. On the other hand, in Korea, the last 2 years, we've been focusing on the development of deep learning models for scan data classification and segmentation. And in the last year, this year, we will develop position and orientation estimation algorithm, and hopefully integrate those classification and segmentation algorithms all together into a scan to 3D model pipeline. So in the end, as a team, UK and Korea, we hopefully want to demonstrate our technology into an international bilateral teleoperation system. For example, we may have a slave system at a race and a master system at Manchester. And these point cloud processing modules like segmentation, classification, and process estimation modules may run either at slave side or master side, or at a separate local server, depending on the computation and communication resources. And so hopefully we will achieve this goal at the end of the year and continue our collaboration. So I think that's it, all I have for today. So thank you for your attention, and we'd like to thank our sponsors, PARC and Korean NRF. Thank you.
Thank you very much, Joaquin and Sungmoon, for a really interesting presentation. It's really exciting to see the potential of this technology to be operated on a global scale, where we have partners on different sides of the world able to integrate into this single demonstration. And I think that shows the real power or potential power of this technology. So it'll be really exciting to see how those final demos come together in the final year of this project.
Thank you.
Thank you.
Okay, so for those who weren't here at the start, we're not going to be answering questions directly after the presentations. We'll be collating them. So if you have any questions, please either keep them for the Q&A session, or you can post them in the chat. I'm collating the questions. I've got a list of questions that have already been asked that we'll be putting to the panel of presenters. So yeah, if you have any questions, please post them in the chat. I'll collect them or save them for the Q&A session. So I'd like to now pass over to Professor Manuel Giuliani from UE Bristol and the Bristol Robotics Lab to give his presentation. Manuel?
Thanks, Simon.
The slides are all shared. Thank you very much.
Okay, so can you see only my slides, or can you see the rest of my screen as well?
No, you're in presentation mode. That's perfect.
That's very good. Okay, so yeah, thanks, Simon, for the introduction, and thank you for organizing this excellent workshop. So I'm going to talk about human-robot interaction for robots in extreme environments today. And so the extreme environment I would like to talk about is the same that Sungmoon and Joaquin have just talked about. So it's the environment of nuclear decommissioning or nuclear facilities. So just to make you aware, nuclear decommissioning is actually a really a challenge worldwide. So just in the UK alone, an official government report says that it will take 120 years to decommission all of the old nuclear facilities, and it will cost around 120 billion pounds. What you can see here is a map of all the sites in the UK that need to be decommissioned in the next 120 years. And a majority of the work that needs to be done is in Sellafield in the north of England. There's also work to be done in the north of Scotland, in Dunray, for example. So all of the old nuclear facilities need to be somehow demolished and decommissioned, and the waste needs to be disposed of. So we think, and we are not alone with this, but so one, robots should be used for this kind of task. First of all, to keep humans away from harm, but also to save a lot of the costs. So we think 10 to 15% of the cost can be saved. And if you think about 120 billion pounds cost or even more, then that's a lot of money. So just quickly, I'm from the Bristol Robotics Laboratory. In case you are not aware, we are the largest multidisciplinary robotics lab in the UK. And we have quite a unique collaboration. So we are a 50-50 partnership between the University of West of England, my employer, and the University of Bristol. And we are over 450 staff, students and businesses. So please have a look at our website if you're interested. There's a lot of interesting robotics work and research that we're doing. And in the past 5 years, we had 2 big projects funded on using robotics for nuclear decommissioning and using robots in nuclear environments. So one is the R&E project. That's a project where Simon and I are working together with the University of Birmingham and the National Nuclear Laboratory. So it's quite a large project with £5 million budget. And then we are also working together with partners in the National Center for Nuclear Robotics. And that's actually a sister project to the Orca Hub and the RAIN Hub that have been mentioned before. So a lot of the work that David showed earlier was sponsored by the Orca Hub. So we are in the National Center for Nuclear Robotics. And again, I would like to thank our funders. It's the ICRA through the Engineering and Physical Science Research Council, with making available such a large budget. Again, £10 million budget is really very much appreciated. So what we are looking in the research that we are doing in these projects from the Bristol Robotics Laboratory part is we are looking at human-robot interfaces and how we design these to control robots in nuclear decommissioning tasks. So just to make you aware, because this is something many roboticists I think are not available of. So there's actually a proven methodology that has been used time and time again to build functional and user-accepted interfaces. And this methodology is called user-centered design. So the idea behind user-centered design is that you start from the user to build your interface. In our case, that would be the operator who will be using a robot in a nuclear facility later. And the goal is to involve the users in three steps in a design cycle. So the first step would be to do a context analysis, where you look at the users, the tasks, and the environments in which the interface will be used. Then you also involve the user in the system design and development, for example, by having feedback sessions and regular meetings with the users to show your interfaces. And you also involve the user in the evaluation. So where you, for example, invite operators from nuclear facilities to use your robots and give you feedback. And all of that is done in a cyclical fashion. So you start as early as possible to involve the user in the design and the evaluation, and you repeat the cycle as many times as possible. And so, as I said, this is a proven methodology. This is not, something that's just a wishy-washy, psychology or design thing. This is something that has been proven to work over the last 30 years. And there's also an ISO standard that you can look up and that describes the whole process in a lot of detail. So look this up. I think this is something that every roboticist should at least know a little bit about. So when we started working in the project, we started with a context analysis of the nuclear industry. And I can tell you this was in that case not very simple, because the nuclear industry is for good reasons secretive, and they don't want to share all of the details of their work, because of course there are also dangers around sharing too much. There are even national secrets that can be shared. So what we did in our case for to find out more about the context of the nuclear industry is, in the first step, we did a literature and media review to understand what the challenges are. Then we also arranged meetings and interviews with different members of the nuclear industry, and we had, unfortunately, we had the opportunity to also visit the Sellafield site and adjacent facilities. So we found out on many things, but just for today, I wanted to share with you. So some of the key findings that we had were that at least in the UK nuclear industry, they always want to have a human in the loop. Teleoperating a robot, they wouldn't allow it to go into a complete autonomous mode without at least a human present. So we also found that there are actually already robots and teleoperation interfaces in use. If you think about the third fact that I have here, so that the nuclear industry in the UK is quite old, and the personnel there is around 54 years in average age, then it makes sense to say, okay, what kind of robots are they already using? What interfaces are they already using to make it easier to train the existing workforce and the new workforce? And there's, by the way, a link to the previous talk by Sang-moon and Joaquin. So one of the challenges that at least the UK nuclear industry has, and I can only imagine it's the same in other countries, is that because of the remote places where nuclear facilities are, there's a recruiting shortage. And by having teleoperated interfaces like the one we just saw in the previous talk, we hope that we will in the future have people working in the nuclear industry without actually having to live near nuclear facilities. They can live in the city centers, in the big cities in a country, and then teleoperate robots in the nuclear industry. So I'm going to give you two examples for the work that we have been doing, where we looked at the old ways of doing things in the nuclear industry, and then proposed or developed a new interface. And the first one I would like to show is very similar to the one we saw in the previous talk. It's about robot teleoperation for nuclear waste sort and segregation. So just to make you aware, so this is what nuclear waste sort and segregation looks like right now. So on the left, you can see glove boxes where the operators handle nuclear materials inside radiation-hardened glove boxes. They have to enter with their hands through the gloves. And of course, there's always the potential that the gloves break, that there are punctures in the gloves, so that there's always a danger of getting radiated as the operator there. And then for nuclear decommissioning of the buildings itself, people have to get into air-fed suits. They have to go into the facility and work really hard to decommission all parts of the building. And just to make you aware, so this is not only that you have to wear a suit, a radiation suit. Also in these facilities, often you have really harsh conditions, 40 to 50 degrees Celsius temperature. There's a lot of dust. Of course, there's the radiation, and it's taking a long time to also get into these suits, in and out of these suits. So, so the nuclear industry actually already uses robots in the UK. So here you can see the box encapsulation plant that has been built at the National Nuclear Laboratory as a test. So, so they use 3 KUKA robot arms that are really heavy, can have a payload of 500 kg, and can open barrels with nuclear waste and can be used to sort these barrels into the right containers. And on the right, you can see the interface that that the National Nuclear Laboratory and Sellafield came up with. So so they use two joysticks, and then they have buttons to switch between cameras. And here you can see a simulation of these cameras where the operator can switch between different cameras. So the operation of these robots is actually really slow because for safety reasons, the operators, they can only move one joint at a time. So they switch between joints, and that's why they have additional buttons down here. Then they move the joint into the desired position. Then they switch to the next joint. They move the joint, and so on and so on. And that takes very long, and you need one operator per arm. So we think that, of course, this is this is now an approved technology that has gone through all the safety requirements of the nuclear industry. But at the same time, it's not intuitive to use. It needs a lot of training, and it takes a lot of time to operate these robots. So what we propose from our side is a solution that looks more like this. So it's a leader-follower system where you have a leader robot that is operated by the operator, and then you have a follower robot that follows the movements of the leader robot, and you use that to sort the nuclear waste, or to pick up nuclear waste and put them into the right containers. And so the advantage of having a system like this is that as the operator, you don't have to think about the movements of the robot. You don't have to think about how to move each of the joints, and it becomes a much more faster and intuitive process this way. So so what we in terms of the research that we did around this this system is, first of all, so we evaluated the system and also the different operation modes of the system. So what you can see on the top here is a user study we just completed in March, where we compared how the robot can be controlled in a manual mode versus the robot working in a semi-autonomous mode. And we also compared the kind of feedback that the robot gives. For example, you can see here on the right, there's a stack of barrels that we had, and we had a virtual force field around the robot that repelled the robot away from the barrels in case the operator was moving too fast or too close to the barrels. And the interesting thing we found in this study is that the people actually, the operators, they prefer the semi-autonomous operation of the robot. So they like when the robot is taking over control, at least partly of the operation. But at the same time, they also report that they would like to have more control over the robot movements while it is in an autonomous mode. And now you can see the autonomous mode in the video here. So we had the operator picking up the object, and then the robot autonomously placed it into the right container. And so this is interesting to see for us, that on the one hand, autonomous robot mode is preferred, but at the same time, operators want to have still want to have control. What we also showed is, and you can see that in the video at the bottom here, and probably you have already looked at it, is that we are able to operate these leader-follower systems without having a wired teleoperation. a wired connection between the two robots. So in collaboration with Toshiba, we showed that we are able to have a smooth teleoperation between both robots, even with a wired connection. And I have to ask Simon, how much time do we have left? Is it only 3 minutes, or do we have 13 more minutes?
You have 3 minutes.
3 minutes. Okay. Well, you know.
Oh no, sorry. 13 minutes. Sorry.
13 minutes. Oh, very good. Okay. All right. So we also looked at, maybe you remember back to the system by NNL. They had different fixed cameras in their system, where their operator was able to switch between the cameras. So we did a study in simulation where we had a similar system. So we compared what it is like for the operator to either have only one camera or two cameras where they can switch, or to have a movable camera. And that's what you can see on the top here in the top video. And again, it's an interesting thing because as someone who's coming from technology, you would think that having several cameras is a really good thing, because then the operators can switch between the cameras and get a better view. And that is true in the sense of the effectiveness of the task, or the precision of the task. So what we found is when you have more cameras, you are able to execute the task in a more precise way. But it is, for the operator, the cognitive workload significantly goes up if you have more than one camera. So from a cognitive workload point of view, it's actually better to have a single camera in comparison to having two fixed cameras. So, but what we also found is that if you have a movable camera, so a camera that moves with the head movements of the operator, that increases not only the precision of the task and the efficiency of the task, but also decreases the cognitive workload for the operator. And that is why we built the system that you can see on the bottom here. So here you have the operator wearing a virtual reality headset, and we stream the images of a stereo camera that is mounted on a third robot arm away from the operator. And let me just switch back the video a little bit here if I can. So yeah, you can see the robot arm that is controlled by the head movements of the robot operator on the right there. So so we have it's basically a camera robot arm that is synchronized with the head movements of the operator. And so we will soon start a user study to properly evaluate this whole system. And I'm just waiting one more minute here to show you the robot, in case you haven't seen it yet. Where's the video? There it is. So here you can see the camera robot in front of the follower robot. And this camera robot is actually synchronized with the head movements of the operator. All right, so 10 minutes to go into the other example. So we have also looked at mobile robot teams and a virtual reality-based teleoperation for mobile robots. So again, to give you a picture of what inspection in the nuclear facilities looks like right now, is so inspection is done by hand, is done by people going directly into the facilities. And there are, inspections, the example on the left here, where you have, a big crane, for example, that needs to be visually inspected, but also with sensors. And then you have situations like the one on the right here. That's a picture from Sellafield, where you see one of the facilities. So as you can see here, how would you go into this facility as a human and inspect it? So there are a lot of pipes. The pipes also need to be inspected from inside. So it's you see, again, we think without robotic technology, it's almost impossible to properly inspect these facilities. So again, when we looked at this, so we found that that the nuclear industry already uses, in some cases, small robot devices for inspection. For example, this is just one example picture. They use these pipe crawling robots, small pipe crawling robots. But basically, the only thing that these robots provide is a monocular camera that can be used for visual inspection. And there are no other sensors mostly on board of these robots. And yeah, so they can be inserted in pipes, but they are lacking. And we directly spoke to operators in the nuclear industry who all told us that the main problem with these robots is that they don't have a depth vision. So it's very hard to determine where exactly, for example, if they find a crack, where exactly that would be in the pipe. So what we were looking at in the Robotics for Nuclear Environment project is how to use a multi-robot team to inspect nuclear facilities. So again, the link to the digital twin here. So before we started using real robots, we did a lot of simulations. So on top, you can see a video where we were able to show that even if you just use one robot with out-of-the-box random path planning, this robot is able to effectively inspect a nuclear facility, in that case, a simulated barrel storage, and to pick up barrels with deformations. We then also deployed these robots in a real setting. So, and you can see that below here. So I'm going to restart the video one more time. So what we found is that if you use robots that are heterogeneous, so in that case, we had 2 robots with different sensors on it, you can actually create a more precise map of a nuclear facility than by just using one robot. So at the end of this video, you can see the 2 maps created by the robots. If you combine the 2, you get a more precise map. And actually, you would think that this is well, for roboticists, creating these kind of maps is not something new. But the interesting thing is that for the nuclear facility, having a map, for the nuclear industry, having a map of all facilities is actually a huge problem, because these old facilities have been closed maybe 20 or 30 years ago, and no one has been in there since then, so they don't have an accurate map of the inside of the facilities. So using robots here is actually something really useful. And the latest work we have been doing, and that is again a link to the digital twin. So once you have robots inspecting nuclear facilities, they will create maps of these facilities, for example, with generating point cloud data. So one of our researchers, Paul Bremner, is looking at how you actually use these point cloud information as an operator who inspects the nuclear facility and tries to determine information from the data. So what Paul just finished in a study is he looked at what information you need in the point cloud data to actually determine correctly the objects in a 3D map. So what he showed in an online study to people is are these pictures that you can see on top here. So he showed on one hand pure point cloud generated data to the participants in the like in the form you can see on the top right here. He also compared it to what happens if you add color and motion to the point cloud, and he compared it to what happens if you turn the point clouds into voxels, like you can see on the below here. And so the interesting thing is that he found that point clouds perform similarly well than the voxel data. So we actually had thought that the voxel data will perform better, but the point cloud performs similarly well for recognizing objects as long as you have the color. Motion is not so important, but you need the color. But the advantage of having point cloud data, and I have a video for that here. The advantage for voxel data is that you that you can then interact with the point cloud data if you turn it to voxels. So here you can see how we switched between point cloud and voxel representation. And the advantage of having these voxels is that you can interact with the voxels, something you can't do with the point cloud data. And that can be used, for example, to tag some of the areas in the nuclear facility. So here you can see Paul tagging some of the areas that are, in our simulation heavily radiated. And just to round this off, one more example of where using digital twins or simulations is really useful. So in a study 2 years ago, we also compared how direct and indirect control of a robot in a nuclear facility is perceived. So here you can see the direct control of a robot where the user is directly pointing to the robots to where it needs to go. In comparison to waypoint control, now you can see it in the video on the bottom there, where the user is just pointing to where the robot should go, and the robot is taking over the navigation autonomously. And so the result here is that we found is that most of the operators, they actually prefer waypoint control. So they prefer the robot autonomously finding its way. But especially if there are communication delays between the robot and the visual representation that they get. But what we also found is that in this kind of operation, you get many side effects, for example, motion sickness. So that need to be managed, and we are working on this right now. All right, so this concludes my talk. So really what I wanted to talk to you about today is to make you aware there is this great methodology, user-centered design, and it is a proven methodology to work to build usable and functional human-robot interfaces. So when you work together with end users in the future, consider the end user needs, the task, and the environments in which your robots will be deployed. And this way you get a better human-robot interface. And I would like to thank the whole team at the Bristol Robotics Lab. So I'm lucky enough that I'm able to present this work. So this is a huge team effort. Also thanks to our collaborators. And no worries, Craig West is not dead. He just wanted to have a black and white photo, so he's still alive. This, I noticed that when I say past members here and saw Craig, then no, he's fine. He's working with Simon now, actually. Finally, to let you know, on 30th of June, there's a free virtual event, the BRL Virtual Conference. So sorry to plug, but if you are interested, we do have an industry focus this year, and there will be really a whole day of work presented about the Bristol Robotics Lab. So have a look at our website for the program. You can drop in and out whenever you want, and just pick and choose the sessions you are interested in. And you don't have to be there the whole day, of course. So thank you very much, and I'm looking forward to your questions later.
Brilliant. Thank you very much, Manuel, for a really interesting presentation. And I think the use of digital twins, it involves so many different aspects, and that human interaction with the robotic partners is going to be critical to that adoption. So it's really interesting to see some of the work that's being done in that area. So thank you very much.
Yeah, thanks, Simon.
If anyone has any questions, please post them in the chat and I will collate them, or you can ask them directly when we get to the Q&A session. So next up, we have Professor Youngsoo Park from the Argonne National Lab. He's going to give a presentation, then we'll have our coffee break, and then we'll move on to the second part. So Professor Park, are you still here?
Yes, hello. Yeah, I'm trying to share my screen.
Okay. We can see that.
Screen.
Yeah, we can see your screen.
Like maximize it. Oops. screen.
We can see that.
Do you see a full screen?
Yep, that's full screen. That's presentation mode.
Okay, good. All right, so I'm Young Park from Argonne National Lab, and today I'd like to give a talk with the title of a digital twin for robotics in industrial applications, scientific automation. I'm sorry, this should be nuclear. Nuclear application and scientific application. And I've been working on robotics and remote system for nuclear applications for almost all my life. And a few years ago, I expanded my scope to non-nuclear area too. So I'd like to introduce that. One of them is scientific automation. So I'd like to introduce two areas of use of digital twins. And starting with the first, the digital twin, I'd like to talk about together what digital twin is. Digital twin, from what I see, is a digital representation of physical system or products. It's a lot used in industries, manufacturing, and also use these terms in all aspects, meaning it covers this simulation of all its life cycle, starting from design, manufacturing, operation, and service and maintenance. And design, we talk about like from CAD design to simulation and how to optimize the design, how to implement the software and simulate that dynamics, as well as hardware implementations. All these are incorporated in digital twin. In manufacturing, it covers the manufacturing process and how to also design for manufacturing, how to CAD/CAM automate the manufacturing process, and how to optimize the manufacturing all. And in operations, like how do we optimally operate, how to enhance the efficiency, how to minimize the downtime, enhance the safety. All these are can be handled in operation part of the digital twin. The fact is the models to be used in operations should be a lot less complex than what's used in design or manufacturing. And also another aspect, this is most kind of difficult robotic task is a service and maintenance. In this environment, it really handles less structured environment. So robot needs to be more teleoperated or autonomous, intelligent, and it's more like a data-driven mode of feedback. Sorry. Sorry, I was kind of messed up with the chart. I was talking about this part, talking about digital twins. Okay. So I was talking like digital twin covers all aspects of the life cycle of a product or physical system. And in doing this, what is really important is not only the simulation model, but it has to integrate other things like Internet of Things, AI, machine learning, and other software analytics to create this digital simulation model that can update and predict better and change with the physical change. So digital twins can be used for fast prototyping, and it can do numerous iterations that's not possible in physical system to optimize solutions. It can be used for training, operation. At the end, it can save a lot of cost and resources. So covering that, so I'm going to talk about like first with a nuclear application. So nuclear application, the robotics and also remote systems are used. And I like to differentiate the different environments. The application can be either in a structured environment, like hot cells, or in this environment, we have a choice of designing the facilities such a way that it can be handled remotely with the remote systems. Or if other environment is unstructured environment, like nuclear decommissioning, waste handling, management, or those are like we don't have a system designed for remote handling. So the robot has to be more adaptive or more intelligent to do the task there. So in terms of that, digital twin technology for both aspects of remote systems to cover those. So going for the first structured environment, this digital twin can be used for making verification of a nuclear facilities conceptual design. So it is possible to build a virtual factory. This is shown our development of a spent nuclear fuel repackaging facility conceptual design. And after the CAD, we made a simulation model of the working model of the environment to test its operation. For some robotic tests, we make more detailed models to test actually touch sensitive motions. And also we implement behind the automation sequence programming to test the feasibility of such a nuclear facility conceptual design. Another use of it will be like using it for training simulator for nuclear facility operations. This is a training simulator used for, this is a nuclear reactor in Ukraine, and it's controlled by plant control system as well as a plant protection system. And we've been developing this along with the conceptual design of this facility. So we had the operation of the mechanical part as well as the thermohydraulic nuclear operations. And we've been simulating that. Now it's this facility in operation. This system is actually also used to operate these nuclear facilities. So it serves dual purpose at the end as operator training as well as operation. Other concept will be some of the in-service inspections of nuclear reactors, which are more routine inspections, can be part of the conceptual design. So in doing that, in certain advanced reactors, like under sodium fast reactors, reactor internals cover under sodium environment, its visibility is very low. So we have to come up with a scenario or a technology to do in-service inspection of a reactor internal. In this way, our simulation and human interactive operation to identify the conditions inside the nuclear reactor is another example of a digital twin for nuclear application. Also, along the digital twin or operation of nuclear reactor, we continuously monitor the nuclear reactor's operation conditions with various sensors. And using the sensors, the digital twin is always incorporating this early detection, anomaly detection module, as well as actually when the automated reasoning system to go into the source of the error to identify the cause of the malfunctioning. So this is process monitoring and diagnostics. So all this design, operation, inspection, and monitoring that can be composed of digital twin for structured environment nuclear operations. So the next step is next application is there are nuclear applications that is entirely unstructured environment, like inspection and maintenance, non-routine ones, and also nuclear facility D&D, nuclear environment and waste management, and emergency response. In these areas, the things are entirely unstructured. So pre-programmed or automated operation cannot work. So here, what's more important is real-time sensing, environment identification, and if humans get involved, conceptual feedback. All these are very important. So in addition to simulation, we have to add this real-time sensing, reconstruction, and augmented reality sensor feedback into there. So in there, okay. So one way of we use that try to come up with an environment is it's argument carry collaboration. We adapted a virtual fixture, which is augmented geometry overlaid on the environment to simplify operator tasks. So as you can see here, in this augmented reality environment with a virtual robot, we have a virtual geometry overlaid on this environment, and overlaid with the 3D sensing of the environment. You can overlay artificial geometries onto that. And this 3D point cloud, we actually made it generate haptic mesh out of it, so we can actually touch the 3D sensed environment models. So to reduce the haptic generation, we made a haptic mesh generation around the haptic stylus, and so we have a fully visible as well as touchable environment. Then we overlay virtual fixtures, and so that it can guide more precise and efficient teleoperation. And the robot follows the virtual. So virtual fixture guides operator motion, and robot follows operator motion. So it closes the teleoperation loop. Another way of enhanced teleoperation, other than virtual fixture, is adding autonomy. Here is a block diagram. It's the same as virtual fixture, but we add autonomy there, behavior-based as well as motion primitives. Add those in there. We overlay with the augmented teleoperation to have the robot do a part of this task as autonomy. For example, we make a straight line along this, then robot compensates the motion along with this sensed geometry of the cylinder, make a circular cut. So those are like teleoperation. The one thing is we implement all this with the basic robot operating system, and using their robot control architecture is used to transfer to different robots. This is our implementation, moving this our enhanced teleoperation method and integrate with their robotic system, easily integrated with the new robot system. And this robot is actually a hydraulic robot shielding, which was used for this dismantling. Okay, that's so far a nuclear application. recently we have moved those technology into digital twin development for scientific application. The main area is a new material development. Development of a new material is a very important technology, has a high economic impact. It's a lengthy process and which requires a special expertise. So it takes about 10 to 20 years to develop new materials. It requires a scientist and also synthesis, experimental scientists, and also automation people. So these are very difficult process. So there was a international consortium advocated use of robotic automation and AI to automate the process to make a self-driving laboratory and by incorporating modular robotic platform. But the key difficult here is it requires a multidisciplinary expert. Like there is a chemist who doesn't know how to program robot. There is a computer scientist who can know how to program robot, but they don't know nothing about the robots. So this is very difficult. And the heterogeneous integration means there's a robotic program as well as operation program and as well as a AI program. Those are difficult to integrate. And each robot system come up with their own APIs. So it's very difficult to integrate. And as you can see, material development covers material design, synthesis design, automation, characterization, sensing and feedback, all of this. That's a very complex process. And it's a prototyping this environment is difficult. So to come up with a solution, we came up with a mixed reality digital twin platform. So mixed reality means like this physical twin. So it covers the physical and virtual environment together. So the chemist and the robotics people can come into the same digital space to develop their process, perform experiment. In doing that, it is possible to rapid prototype end-to-end process because we don't have to build everything from hardware. At the end, we will democratize this material development. Now, these material labs, who can only a few can access from the world, can have their own lab on their desktop. So having this, it's like a 3D printer. Now we have a 3D printer. We can manufacture things on everyone's desktop. So we can develop new materials on everybody's desktop. So that's our vision. The key to our innovation is we like to provide some software framework for such development because even Argonne has a various materials lab imported robot system. They all have different hardware, different APIs. So everybody has to develop their own. Also, this developer also has to go into this hardware development. And so we like to develop this framework, software development framework based on Rust. So developers only can focus on, don't have to develop the robot operation, but that application for the scientists. That's more like the actual, the robot operating system or the computer or cell phone OS does. So using that, we are testing some of them, like we have an operator to do some experiments and send it back to take the motion primitives. And then based on motion, the actually perceived environment, we can operate the motion primitive. So this has a, it's just a beginning stage, but the chemists, rather than doing programming, they can do actual experiments. Then the the experimental robot system can do actual operation. Okay, so summary. So I've covered the digital twin is a digital model of a physical system, but enhanced with the data analytics. And to cover the unstructured use of nuclear environment, we added a mixed reality component to it. And also we provided a RAS-based development framework so that developers don't have to do robotic programming anymore, but only focus on their application programming. So we have shown some needs or cases for this mixed reality digital twin for nuclear applications for structured and unstructured environment. Also, our recent work on self-driving laboratory. So this scientific automation is they have not been automated at all. It's very recently emerging, and we see a lot of opportunity for using a digital twin. Okay, that's all my presentation. Maybe I ran over somewhat. Yeah.
No, that's not a problem. Thank you very much for a really, really interesting presentation. I think you touched on some really key points about the complexity of these digital and physical twin systems, and especially that connective digital tissue, that cyber physical fabric that Professor Lane was touching on at the start, and actually things like standardization, modularity, ease of use when you've got multiple different technologies all trying to come together. I think they're really interesting points for discussion. And that concept of maybe, it's mixed reality that we're trying to envisage, and some really interesting applications as well. So thank you very much for the presentation. So what we're going to do now is have a break. So we'll have a 15-minute break. I'd like everybody to come back. So it'll be 11 o'clock GMT. So in 15 minutes time, I'm going to open up 20 breakout rooms, which you can drop into if you wish to have side conversations or have chats with people. Those sessions won't be recorded. We'll come back in 15 minutes time. We'll have our final presentation from Professor Luca Carlone from MIT, and then we'll move on to the panel Q&A session. So I'm going to pause the recording now, and I will see everybody in 15 minutes. Thank you very much.
Our work on algorithms to build mental models for robots and autonomous systems. I'm Luca Carlone, I'm assistant professor at MIT. Maybe a good way to get this presentation started is to present a single slide overview of the work in my lab. So I'm the director of the Spark Lab at MIT, the Sensing, Perception, Autonomy and Robot Kinetics Lab. We work in the broad area of robotics and autonomous systems with specific focus on robot perception and computer vision. What you see in this slide, along the columns in this slide are the three big research lines that we work on, including robust and certifiable perception. We have a long history of working in visual inertial navigation, simultaneous localization and mapping, and certifiable algorithms for object detection. We have a line of work on high-level scene understanding, and this is going to be covered in this presentation. And then we have another type of work which is on co-design, which is not only on perception, including perception, communication, and control. So the plan for today is to cover two topics, two line of works my group has been working on. The first is Chimera, which is our effort to go from simultaneous localization and mapping to metric semantic mapping. And then the next step is to present this idea of 3D dynamic scene graphs, which is about taking a step farther from metric semantic mapping to real-time high-level understanding. And this is amazing work of students in my group, which you see here: Tony, Marcus, Arjun, Yoon, Nathan, Jingnan, and Andrew. So I would like to start with Chimera. And I want to start first of all by saying that we have to be proud as a robotics community. We have to be proud of the progress we made over the last 2 decades on simultaneous localization and mapping. Thanks to the research we have made, we now have real-time open source systems such as OrbSLAM, reconstructing sparse feature maps of the environment. We have approaches making denser reconstruction as DSO, and we also have approaches for SLAM, which are using novel sensors such as event cameras. And all this research is steadily transitioning into applications. For example, visual navigation and SLAM is used on the SkyDR1 drone, and the same technology as we have seen in previous presentation is used also for virtual and augmented reality. And there are many companies looking at startups capitalizing on these ideas and maybe doing hardware implementations of these ideas, including Artisan, SlamCore, and the project we made a while ago on designing a chip for visual navigation. At the same time, we have to realize that there is still a large gap between robot and human perception. So for robots, right now we're getting pretty good at designing algorithms that allow a robot to build a sparse or dense representation of the environment, let's say a point cloud or a voxel-based representation. Or in alternative, we can have robots build a collection of object-based maps. At the same time, as humans, we do much more than that. For example, I can show you just for a second this image. You can stare at it for a few seconds. And just from a single image, you can form a complex mental model of this scene. You can understand the geometry. This is a street. There are buildings near the street. You can detect the cars. You can understand also the semantics. For example, you can understand that the yellow cars are specific type of cars, that they are taxis. And you can even reason over the relation among objects. For example, one car is following the other, or maybe some person here is trying to cross the street. Okay, so this type of complex understanding of the environment is something that we are still missing in robotics. So why do we care about high-level scene understanding to start with? Well, the first reason is that high-level understanding is really key to interaction. In the future, I don't want to tell my robot, go to position X, Y, and Z. I want to tell my robot, go and grab me a cup of coffee, or I want to tell my robot, go and grab this specific object. And the robot needs to have a complex understanding of the environment in order to execute over these high-level commands. Maybe one example, which is expressing this need for high-level understanding. Imagine that I would like to have a future Alexa in which I'm asking Alexa, where did I leave my coffee mug? And Alexa has some awareness of space such that it can answer that my mug is on the table near the window in the dining room. And of course, that's with the current technology is not possible. Alexa will have no idea about the spatial configuration of the environment. High-level understanding is also key to robustness. Here in this slide, I'm showing you what you recognize as a car. At the same time, if I show you the full picture from which the car was cropped, you can stare at it for a few seconds. Then you can realize that actually there is no car in this image. There is just a car painted on a van. And probably your mental model has been something like this. You have been detected ground, you have been detected, you detected a car, you detected a van, and then you reason on the fact that these two objects cannot be on top of each other. So you're able to figure out that one of the two was painted on the other. So essentially the message here, as I'm saying in this slide, is that robust perception relies on simultaneously understanding geometry, semantics, physics, and relations in 3D. And of course, there are practical examples in which this incapability of current algorithms to reason over geometry, semantics, physics, and relation is indeed inducing failure modes. So these are common neural networks in which easily you can induce the neural network to fail just because the neural network does not have an overall high-level scene understanding. What I'm going to present in terms of our contributions are the effort we made in making progress in getting robots to develop high-level understanding of the scene. And the first step is really was really to combine geometric understanding with semantic understanding. So our contribution, which is something that we have developed over the last 2 years, is what we call IMR, which is a real-time metric semantic simultaneous localization and mapping library. So Chimera takes as input sensor data from a camera. So you can imagine that it's a stream of images, and there is also an inertial measurement unit. And it's producing as output a 3D reconstruction of the environment. So what you see here is not like flat video, but it's a 3D mesh model. And you can see a top view of the mesh model on the right. And here the robot not only is able to build a 3D mesh model of the environment, but the mesh model is also labeled with different colors. These are false colors. They actually correspond to semantic classes. So for example, in this visualization, gray, of course, corresponds to the ground, dark green corresponds to the wall, yellow are the cubicles, and so on, such that the robot can at the same time reconstruct the geometry, but also get a semantic understanding of the objects in the environment. And if in order to build digital twins and so on, you're using this kind of SLAM technology, you may also take a look at the code. We have a very good open source implementation on GitHub. So in the next few slides, I want to tell you what's inside Chimera. I want to tell you about it's a modular library. I want to tell you about the building blocks inside Chimera. And then I want to tell you a little bit about the results we are getting by testing Chimera. So Chimera is including 3 key modules. First of all, we take data from a visual inertial sensor, a camera with an IMU. And there are 3 key modules in Chimera, which you see listed here. There is Chimera Visual Inertial Odometry and Chimera Mesher. There is Chimera Robust Post-Graph Optimization. And there is Chimera Semantics. And I will go over the next slide. I will cover each one of these modules. So Chimera VIO, as the name says, is about visual inertial odometry. In visual inertial odometry, imagine that you deploy a robot in a completely unknown environment, and the robot is trying to build a 3D sparse representation of the environment. So if you see at the beginning of this video, the robot is extracting key points in the image, and is trying to map these key points in 3D using what is called the visual inertial odometry algorithm. And at the same time, it's trying to figure out its own trajectory, which is the one that you see, the reference frame that you see moving. And in Chimera, not only we build a sparse map of the environment, but we also reconstruct this mesh that you see here. And inside, behind this visual inertial pipeline, is the idea of IMR integration, something that we proposed back in 2015, which is allowing to get very accurate trajectory reconstructions while keeping real-time performance. So in Chimera, we typically have we can estimate keyframe poses at around 20 Hertz, and we can also have faster IMU-based pose estimate at 100 Hertz. And we also have a number of ideas about, we have implemented a number of ideas about structureless projection factors, which are making the estimation process particularly robust. So out of this, we get an estimate, an odometric estimate of the trajectory of the robot. Unfortunately, as you know, all the odometric estimates are diverging, are drifting over time. So the second step is really to enforce this idea of loop closure. So imagine that there is a robot starting at this point and driving around in the environment. With just the odometric estimate, which is the one in red, the odometric estimate will drift over time. But at the same time, we can recognize that 2 places, we can estimate the relative pose within 2 places, 2 distinct places. This is what is called a loop closure. And by enforcing loop closures in the reconstruction in the SLAM reconstruction, we can reduce the drift, we can reduce the error that we commit in estimating the trajectory. So in Chimera, we have a loop closure detection approach, which is based on standard bag of words with ORB descriptors. This is fairly common in the state of the art. It's similar to what is used in ORB SLAM. The key insight is that we have a particularly sophisticated post-graph optimization approach, which is the approach which is used to get an estimate of the trajectory, including loop closure. And in particular, we have a robust post-graph optimization approach, which is able to reject bad loop closures using an approach from Mendelssohn proposed in 2018, which is called pairwise consistency maximization. So pairwise consistency maximization, we look at the cycles in this graph to figure out if a loop closure is accurate or not, and we reject bad loop closures. Bad loop closures will show up all the time because different places may have a similar appearance, which is inducing place recognition and loop closure detection to fail. So just to tell you something about the impact of this loop closure rejection approach, if we perform post-graph optimization without rejecting loop closures, we get the trajectory on the left. Now, I'm not showing you the ground truth, but you can see that this trajectory is really like, noisy, and indeed is quite incorrect. If instead we enable our outlier rejection approach, we get a smoother trajectory in which we identify that actually only few of these measurements that you see in blue are correct loop closures, and we discarded the others. Okay, so out of Chimera VAO and Chimera robust post-graph optimization, we have a very good estimate of the trajectory of the robot. And again, remember that the robot is moving in a completely unknown environment. And the last step is Chimera semantics, which is about getting this 3D model of the scene, including geometric and semantic aspects. For Chimera semantics, the basic implementation is based on vox blocks, which is an excellent library from ETH, which is using a voxel-based representation to build a mesh. What we add to vox blocks is really the semantics part. The semantics is about taking a 2D segmentation from an image and projecting this 2D segmentation back using ray tracing and a Bayesian update. This idea of Bayesian update is something that has been used in the literature in the past, but what we do is that we develop an efficient implementation which is able to run this ray tracing approach on CPU and very efficiently. Instead, typical approaches are based on are computation heavy and are based on GPU computing. So despite the fact that we are running on CPU, we can run these at 10 Hertz on a standard CPU. So an idea that I want to present today is something that is recent work that we've done over the last several months, which is an extra block in Chimera, which is adding extra functionality. And I want to present this today for the first time. It's called Chimera PGMO, Postgraph and Mesh Optimization. And this module is addressing a specific shortcoming that we had in the original version of Chimera that we released back in 2020. Essentially, what happens is that Chimera VAO, the visual inertial odometry part, as I mentioned, is drifting over time. It's an odometric estimate, hence is drifting over time. And the drift, as I mentioned, is also typically corrected using loop closures and robust postgraph optimization. So the visualization is this one. You have an odometric estimate in red, which is drifting over time. And thanks to this loop closure, you can kind of bend it, you can kind of correct the trajectory estimate just to enforce the loop closure, which in this case is the measurement in blue. So the issue that we try to face here is that the 3D semantic mesh is actually built in Chimera, is built from the VAO estimate. Okay, so the issue is that the mesh itself is kind of drifting over time because it's based on an estimate which is accumulating error over time. And the question is, how do we make a 3D mesh model which is instead globally consistent? So far in this slide, I'm saying that we can kind of correct the postgraph, but so far we do not have a way to correct the mesh. And we developed this idea of postgraph and mesh optimization, which you can find in the journal version of the Chimera paper, which is indeed able to correct the mesh itself. I'm going to give you an overview of what Chimera postgraph and mesh optimization does. So the input to PGMO, again, postgraph and mesh optimization, is the original odometric mesh. So this is the mesh which we integrate from the VAO estimate, which is accumulating error over time. We also have as input the odometry, of course, of the robot from the visual inertial odometry, and the loop closures that we detect with the loop closure detection module. And the output of Chimera PGMO is a globally consistent 3D mesh. So how do we do this? Well, the key idea is use a tool from computer graphics, which is called deformation graph, which was proposed a while back for different application in computer graphics. And the basic idea is that you start with a mesh and with an odometric trajectory of the robot. Out of these, you build a deformation graph. A deformation graph is nothing else than a subsample version of the mesh in which you attach local coordinate frames, which are the one that you see in the violet here. And we also add edges between nearby nodes on the mesh, and also between the robot pose and the mesh itself. So the deformation graph, you can think about it as a collection of poses. Part of these poses are attached to the trajectory of the robot. part of the poses are attached, are forming local reference frames attached to the mesh itself. And remember that the mesh vertices will be hundreds of thousands, will be very large mesh. But in this phase, you can just downsample to a small set of poses. And after we built this collection of poses and edges, is essentially a graph, what we can do is that we can enforce an extra constraint, which is the loop closure, this one in blue. And we can deform at the same time both the trajectory of the robot and the mesh itself. And the result is that, of course, not only we have corrected the trajectory in red, but we also have deformed the trajectory to be consistent. We have deformed the mesh to be consistent with the trajectory. So what we do in the paper is also to show that this idea of deformation graph is actually mathematically equivalent to post-graph optimization, which is the problem of just estimating the trajectory of the robot. And the good news about that is that post-graph optimization is a very well-studied problem for which there are a number of fast solvers that you can use. So it was very nice to see that actually the mathematics is the same as this very standard problem. So just to give you an insight of how this works in practice, I'm using this animation to show this a top view of a map. The robot, I think, is starting from here, is traversing all the map, and is coming back to the original location. At the original location, there is a loop closure. And what you see in this animation really is the process of correcting the mesh. You see that after the loop closure, the mesh is kind of jumping around just because of the post-graph and mesh optimization. And on the right-hand side here, you see what happens. You see a 3D reconstruction of an environment with the color being color-coded by the error. And you can see what happens before the deformation with the post-graph and mesh optimization, and after the deformation. And you can see that essentially the color becomes much, the dark areas essentially disappear, meaning that the error in the reconstruction goes down because of the post-graph and mesh optimization. And the post-graph and mesh optimization in the Chimera architecture essentially is something that can replace the post-graph optimization. We can just put this other module to replace the original post-graph optimization. So you can find plenty of details in the paper, but what I want to stress here is that we have been doing extensive testing of Chimera, and we're still in the process of doing more and more testing. We would like to release a version 2.0 of Chimera in the next few months. But what we've been busy with over the last several months was real testing and extensive testing, both in real environments and in simulated environments. So here you see a bunch of environments we tested in: apartment environment, Europe dataset, school environment, and MIT Aeroastro. We have photorealistic simulations in Unity. We're doing a lot of testing in these simulations. And in general, we've been trying to deploy Chimera in a number of different sensor configuration or robot configuration. So for example, we built a handheld sensor at MIT. We've been testing on the Europe drone, which is a data set. We've been testing on self-driving cars. Cannot say much more about these. We've been testing some modules in Chimera as part of the DARPA Subterranean Challenge on a Husky robot. And with the Army Research Lab, we have been testing on the Jackar robots. So again, for the details on the experiments, I will point you to the paper. I want to show you just this slide as a summary of the type of results we get. Here is a slide about average trajectory error. So this are the errors committed when estimating the trajectory. So the lower, the better. And we are comparing different approaches for visual inertial odometry and post-graph optimization along the columns for different data sets on Europe. And what you see here in boldface are the approaches achieving the smallest error. I would say that other approaches such as Beans-Mon, they are very competitive. But with VIO, with Chimera VIO, we get good performance and we get slightly lower errors. In general, in other data sets, I would say we have comparable errors. But with the post-graph and mesh optimization, we can bring this error down even farther because of enforcing loop closures and enforcing loop closures over the mesh. So the message out of the experimental evaluation that we have been doing is that Chimera VIO, which is the visual inertial estimator, is getting a very good estimation performance with a drift around 0.2% of the trajectory traveled. We have an approach which is robust to incorrect loop closures, although we're doing even more work, we have more ideas to further improve that using another approach that we proposed, which is called graduated non-convexity. We have this new approach, which is the post-graph and mesh optimization, and we've been showing that this actually improves the quality of the 3D metric semantic reconstruction. And the other good news is that Chimera is running in real time, thanks to a very efficient multi-threaded implementation. There are the time statistics over here. I will not go over the details, but you can see that there are multiple threads running. I think actually this is, there are just 3 threads running here, but you know, that they're split into the different modules. And you can see that everything is running like, you know, in the ballpark of like, you know, 50 milliseconds or so. And the important things like, you know, that must run at frame rate, they're running at frame rate. So everything is real time. So another recent approach that we made is to think about a multi-robot version of Chimera, which is something that we call Chimera Multi. I don't want to spoil it. This is going to be presented at this ICRA, I think in the next few days. But essentially, this approach of the deformation graph and the trajectory estimation applies to the case in which there are multiple robots moving around in the environment, meeting each other and try to build in a distributed way a 3D metric semantic mesh of the environment. So here what you see is a top view of a pretty large outdoor environment. And you can see a metric semantic map with the semantic classes being this one on the right. Again, I will not say much more. If you're interested in these, attend this session at ICRA, and my student Yun is going to tell you everything about this approach. In the last few minutes of this presentation, I will cover the second part of this presentation, which is 3D dynamic scene graphs, which is about taking Chimera one step further. And I will try to leave also like, you know, a few minutes for questions at the very end. So the 3D dynamic scene graphs are essentially a new map representation, are what I call the mental model for robots. The basic idea is very intuitive. So a scene graph is a hierarchical map model in which the lowest level of the hierarchy is what is typically the output of SLAM. Is a metric semantic, is a map model, is a mesh model. So at the very bottom of this hierarchy, you can see this metric semantic mesh. But on top of that, we also reconstruct other layers, and that's why it's a hierarchical representation. In layer 2, we have objects and agents. So here we estimate the location of objects and humans moving around in the environment. In layer 3, we figure out places and structures. Places are just free space places in the environment. Structures are walls, ceiling, and so on. And then we go up in the hierarchy, reconstructing rooms, buildings, and so on. And we can just build this hierarchical abstraction, a hierarchical map of the environment. So a little bit more formally, a dynamic scene graph is a directed graph where nodes are spatial concepts, which is anything really grounded in 3D, objects, agents, rooms, and so on. And edges represent spatio-temporal relations between concepts. For example, agent I is in room J at time T. And the basic idea here is to describe the environment at different level of abstraction, to capture things which are moving, agents which are moving in the environment, and also include actionable information for planning and decision making. For example, the places are collecting free space location in the environment, and they can be used for fast planning. So not only we've been proposing this idea of dynamic scene graph, but we've been working also on developing algorithms that can build a 3D dynamic scene graph from visual inertial data in heavily populated environments. And in hindsight, really what we are proposing here is kind of a transition, a shift between traditional SLAM algorithms to what we call spatial perception engines, which are algorithms which are able to infer the geometry, semantics, and high-level spatial concepts and their relations in real time. And here, what you are looking at in the video is the type of environment that you would like to work in. Crowded environments in which you want to build a complex map model for the robot to interact with the environment. I will go quickly over the layers just to leave a little bit of time at the very end. Layer 1 is, again, the metric semantic mesh, and this is essentially Chimera, is the first part of the presentation, which is building this 3D metric semantic map with some extra cleverness about how to handle dynamic objects. You don't want to include dynamic objects as part of the 3D reconstruction. You want to keep them outside the 3D reconstruction. The second layer is about the objects and agents. So for this layer, I think we are the first one providing this kind of dense metric semantic reconstruction, at the same time estimating the dense pose and trajectory of humans. And to do that, we essentially take the image as input. We use human pose estimators based on deep learning. We're using graph CMR, which is a state-of-the-art approach from the group of Kostas Danilidis. And on top of that, we include some tracking over time to make the pose estimate of the humans consistent over time, and also to reject outliers. And the result is that we have these tracks in which we know exactly over time how the human is moving. And again, in this layer, we also have objects. We distinguish objects with a known shape from objects with known shape. For objects with a known shape, we just fit a bounding box. If we have a CAD model of the object, we fit the CAD model into the point cloud using an algorithm that we proposed in previous work. It's called teaser++. For places and structures, again, places are just obstacle-free location in the map. It is a graph of obstacle-free location in the map. And this is based on an existing approach from ETH, which is about creating a skeleton of the environment in 3D. And this is a graph of free space, which can be used for planning. And the structures is walls, again, ceilings, and so on in the environment. In order to extract rooms, again, I will go quickly over the details. You can find all the information in the paper as well. We apply a clustering algorithm, which is taking the graph of places and is clustering the graph of places into different rooms by looking at the ESDF, which is the Euclidean science distance function, which is a kind of information about the distance to obstacles. And this way we can identify that there are different rooms, and the robot can understand the presence of different rooms in the environment. And buildings, we didn't do much, in this case, a single building reconstruction. So everything will end up at the single building node. But I'm taking the opportunity in this slide to just give you a zoomed in version of the second layer in the dynamic C graph, which is including objects and agents. And you can see how this model can be useful for situational awareness, to interact with humans, to execute high-level commands from humans. It's kind of the mental model that we really should be pretty intuitive for us as humans. So I had a few extra slides, which I will skip actually, but we have real-world reconstructions of the scene graph and also reconstruction in photorealistic simulation. This is not real-time yet. It's something that takes, at the end of the run, it takes around 30 minutes for a robot to reconstruct. And in the paper, we're also showing an example of how to use the scene graph to perform essentially hierarchical, very fast hierarchical path planning. So I will conclude here, and as a summary here, I think in this presentation bottom line is that there is still a large gap separating robot and human perception, and we need to go beyond SLAM and to think about real-time 3D high-level understanding. In this presentation, I cover two ideas which I believe are shooting in that direction. The first one is Chimera, which is a real-time metric semantic visual inertial SLAM library, which is modular as visual inertial SLAM mapping semantics, and also cover in this presentation new ideas such as post-graph and mesh optimization. And then in the second part of the presentation, I cover this idea of 3D dynamic scene graph, which are a general representation for robot perception and spatial AI. So we'll conclude here by thanking you for your attention, thanking the sponsors supporting this work. And if you're interested, you can follow us and essentially look at our work through papers and on the YouTube channel. Thanks for your attention.
Brilliant. Thank you very much, Luca. That was a really, really interesting presentation and some fascinating technology and demonstrators. And I think it really shows the complexity of how these systems are going to have to be developed, or to the level that they're going to have to be developed to enable the capabilities that we're almost assuming and wanting out of these robotic systems. It's not as simple as going, I've got a SLAM system and it now works. Humans are very complex beings, with untapped and unparalleled cognitive capabilities that we want to install in robotic systems, and that's going to be a massive.
And as you see, as you see, Simon, the point is exactly that. As humans, these capabilities are so easy and so seamless and effortless that we give them for granted for robots. But actually, robots are not able to get those with the same level of high level understanding or even real time performance that we do as humans.
Okay, so thank you again, Luca, and thank you to all of the presenters this morning. We're now going to move on to the panel Q&A session. So I'd like to ask the presenters to turn their videos back on. I've been collating questions throughout the session, and we would welcome any other questions during this session. So far, the questions have kind of been split into two categories, specific technical questions and then more general broad questions. So I'm going to start with some of the technical questions that are picking up on particular elements of those presentations. And then I'll end with the more general questions, which will lead us into our mind map breakout discussions. And as I've said, if people have other questions that they'd like to ask, please raise your hand in the participants menu and we'll take it from there. So we'll start with a question to Luca on your presentation. So this is from Hyunji Chang. Do you see a place for LiDAR, stereo, RGBD sensors for building 3D dynamic scene graphs? These sensors are known for making more accurate geometries than mono cameras and mono vios.
Yeah, it's a great question. I think we mentioned also that in the conclusion part of the scene graph work. What we see there is that we propose this initial idea and this initial representation, but we see that as a starting point, not as something that is solving really high level perception. And indeed, one of the potential avenues is just to see how much we can push 3D reconstruction and metric semantic understanding through other sensors. LiDAR is of course a great candidate for that, just because as the question is mentioning, just the quality and the accuracy and the range of the sensing is particularly useful for 3D reconstruction. So the short answer is yes. At the same time, imagine that the choice of sensor will depend, of course, on the application, right? So for example, in a lot of the work we do, we work in two domains, I would say, self-driving cars and drones. For self-driving cars, it's probably a fair option to put more sensors just to get better models. For small UAVs, that's not an option. We do not have the payload to mount a LiDAR on the drones, and that's why we have to push a lot for vision-based. But definitely, having a larger field of view, longer range, and combining information from LiDAR and vision can be a great infrastructure for dynamic scene graphs. LiDAR only is a little bit more challenging, just because getting the semantics from LiDAR only is more difficult. So imagine that still a camera must be in the loop for that kind of reconstruction.
Okay, thank you very much. So there's a question from Matter, which I'm actually going to open up to the entire panel, because I think several people can have inputs to this, and that's about latency. So we saw several presentations about teleoperation of robots, be they anthropomorphic manipulators or the mobile robots. What's the influence of latency in the operator's experience, and how can digital twins be used to improve the operator's experience for this matter? And kind of the build on to that is, is there a distance? Are there distance limits to that? So if I go to Joaquin and Sungmoon first to discuss this one.
If you just use bilateral teleoperation with haptic joysticks, I think that up to 100, 200 milliseconds is something that a human can cope with. Stability starts to deteriorate, so basically you need to generate a lot of artificial forces to make sure. So you lose the transparency between the master and the slave. If it's bigger than this, your problem is not only the transparency or whatever, it's just that it is very difficult for the human to stay in in the loop, I think, is my personal experience. Ideally, what you would like to try to do with this digital twin is avoiding this, because you will have a digital twin in the master to avoid this kind of delay in the communication. But always, if this can be done efficiently for the operator is a big question on until which point. I think Manuel was speaking about this, not the cognitive load of the operator increase, and it is a challenging problem. Maybe you solve the mathematical problem, but then you give to the operator a very difficult issue to deal with. It's my personal opinion.
Thank you. So Manuel, would you like to add anything to that? Manuel.
I'll let Sangwon talk first, but I think his microphone is muted. Sangwon.
Okay,
yeah.
so sorry. Okay. So, I mean, the reason Joaquin and I proposed a project on the digital twin-based teleoperation was to eliminate the effect of the delay between master and slave. So the operator can interact with digital twin on the master side. They can eliminate the delay effects. And the key point is how effectively the digital twin can replicate the remote environment. And that, I think, the fidelity of the digital twin is critical for the this type of digital twin-based teleoperation.
Yeah, I mean, I could just add, I mean, the question was whether whether a digital twin can help with the delays. So I would say yes. I mean, our research shows that if you have autonomous operation of the robot, that decreases the cognitive load in case of delays. In our study, we had up to 2-second delay, by the way. So so that's quite considerable. So I would say if you have a local copy of the digital twin at the teleoperator site that shows, for example, the plan of the robot, that could probably help. But that, you know, of course, needs to be updated constantly. Also, the delays we have found so far in the technical implementation didn't come from the robot control. The delays in our case always came from streaming video data from the robot to the teleoperator interface. So just to keep in mind, you know, it's less the robot control. It's other factors that we you know found are causing delays usually.
David, bring you in at this point.
Hi, thanks, Simon. I'm going to make 2 comments. As you know, Simon, we did some of this kind of remote teleoperation stuff with force control and haptics as part of the sort of ICRA Rain Hub digital tissue stuff we did last year. And I was quite impressed, first of all, by the way people were mucking around with, it was over the internet, right? So mucking around with the protocols, UDP and TCP/IP, and actually you can squeeze a bit more out of it using UDP, if I remember rightly. And there's some secret voodoo there that various startups are hiding, you know, in order to, you know, make it more possible. But I think it showed that with typical delays over the internet, it was possible to do tactile work. Certainly with UK internet, maybe if you go international, it's different. So that was quite encouraging. The other point I wanted to make was around, I noticed Scott Reed's on the call from CBite. I won't embarrass him by bringing him onto the chat, but probably 10 years ago now, we were doing work with AUVs, autonomous underwater vehicles, where the vehicle's remote, you've got an acoustic modem to talk to the surface, and that's got 2 issues. One is delay, and the other is bandwidth. And it's not quite as bad as Mars, but it kind of feels like it sometimes, right? So how did we deal with that? Because we were getting status updates from the vehicle, but they were out of date, and actually we'd lose the link for a while. And all you've got on the surface about what's going on down below is effectively a digital twin. You're running a model of the vehicle with everything, the planning system, the control, the lot. And we built a system called the Back to the Future engine, I remember. And It was great. So what we could do is you were viewing the digital twin, the real vehicle. It was lagging behind the real vehicle and what was going on, and during periods of blackout, you could predict what was going to happen because you knew what the logic on the vehicle was, what the planning system. But what you didn't know was what was the vehicle encountering while it was down there. So the longer you left it, the more drift you'd have on the vehicle's movement. And if it, for example, encountered an obstacle and went around it, you wouldn't know anything about it. Or if it found something interesting to go and look at. So some of the smarts on it were hanging around to go make measurements because it was an interesting scientific area or a bit of oil rig. So the challenge then became when you get the link back, what do you do, right? Because the version you've got of what's going on is different to the one that the vehicle's got. And the first things we did was just update it, bang. And so the screen changed and everything changed. And not just the position, but also the sort of mission plan stuff that tells you what the vehicle's doing and why it's doing it. And that was completely disorienting for the operator, right? Because there's, whoa, what happened there? I don't know. So we experimented with various ways of smoothly updating, the change in the vehicle from where you thought it was to where it is. And we found that actually worked. It's quite simple workarounds worked quite well. So I think my high level point is you can do a lot with delays. If you're doing teleoperation, haptics, yeah, you've got limitations there, obviously. But even if you've got quite long delays, by using digital twins, by being careful about how you update the real situation with the digital twin, you can have a good sense of what's happening and make it usable. Thanks.
Thank you. And that actually leads us kind of towards our next set of questions about that digital tissue element. So, one of the elements, we've got to connect these digital twins to the physical twins. That will lead to delays, that will lead to a variety of other challenges. David, you used the term cyber physical infrastructure, cyber physical fabric, digital tissue. Amata has asked, who's going to be the owner of this? So, we want the vision is of a connected world. That I think you mentioned at the start, the global digital twin of things. You've got federated digital twins. You use the example of the aircraft engine, the airport, the baggage handling system. All of these interconnected systems. Who is going to invest in this infrastructure? Who is going to own this infrastructure so that it becomes usable?
That question for me.
We'll start with you, but I'm happy to open this up because I think this is a fundamentally challenging question.
So the model is the internet and the web. Who owns the web? Who owns the internet? Used by everybody, owned by nobody. And that you're able to do that because of standards. It's so that when people develop stuff, software, web pages, they conform to standards. And so, okay, so how does that come about? I think the best examples, and there's a big debate about this. If you go and talk to the data science community about this kind of thing, they very much see it as a sort of almost a philosophy challenge. And that they have this sort of philosopher's view that you build a data model, which explains it all. And that's a very sort of computer science view. If you go and talk to engineers, and many of us on the call here who as roboticists probably think of ourselves as engineers, maybe not everybody, they have a much more sort of agile approach to how to do things, right? Which is sort of, sprint, fail, rebuild, sprint, and move forward on whatever cycle time of your sprints are. And so you sort of build an MVP and then that doesn't work and you need to extend it and so on. And I noticed Young Park was mentioning earlier the use of ROS as one of the ideas for, what you were talking about, Young, was very similar, but had some similarities. And ROS, has a large element of open source around it. But I think there's the potential for an open source to start the process of building some of this infrastructure that we need. And then there are plenty of good examples of situations where open source has then been turned into commercial products. I mean, the prime example is Red Hat from Linux, and the Red Hat company did very well, venture-backed. But there are other examples with Apache and Miso for cloud infrastructure coming out of work at Berkeley. So, you can take open source stuff and then have it turned into sort of, commercial product that then everybody uses. So there's a variety of mechanisms. The starting point, I think, is the community. Now, whether it's the jury's out, how do the computer science philosophers around the blackboard building the data model, interact with the engineers who want to sprint and develop and fail agile? That's a different one, and I don't have the answers to that yet, but I think that's part of the starting point. Thank you.
Thank you, David. Would anyone else like to come in on that point before we move on?
Yeah, I'd like to mention, this is Young Park, mention one thing. We've looked into like connecting this virtual world. RAS has it works in the local network. Now we come up with a more larger universe, like a metaverse. We can build it, meet in the common space in like a video, like internet games. Then we do need to come up with a new communication tools, maybe a Unity, UNet or something, but nothing like that has not yet been done. So thing is, robotics is it's like a very primitive time of computers or internets, computers or cell phones. Those things already have a well-developed operating systems that we can develop applications on top of it. Robots, everybody works from the hardware to the end on their own. When they switch to something else, they have to develop, get used to new hardware, new API. So there's no standard. So it's very difficult work for the developers. So RAS has come a long way in like speeding up developments, but on top of it, for broader universe, right? That also requires a new tool for that.
Okay, thank you very much for very interesting points there, and I think that's an area that we can discuss in the breakout session later. I think that's quite a rich topic for discussion about standards and the open source nature of the technology and how we adopt that. I'm going to move on to a question from Chris Kidd, who's asked, a lot of impressive simulation work is going on within the digital twins. However, it's only effective if it can be validated by physical testing in real environments. He'd like to ask the panel's view if they think there's a bit of a disconnect. There's lots of simulation work, but there's a lack of subsequent physical testing. As an industrial end user, what do you think you need from industry? What does academia need to help pull these together? And I'd like to start with you, Young Park, because you showed some really interesting work on the mixed reality, where you're using that digital and that physical twins. So what are your thoughts on that?
Yeah, so as I mentioned in the beginning of my presentation, I think digital twin has covers whole life cycle of a physical system, from design and then fabrication, manufacturing, and operation and maintenance, right? The first three, design and manufacturing, even most of the operation doesn't really need to synchronize the real world and the virtual world perfectly. We can do a lot of simulations to do a lot of iterations for optimization or even training, right? Only the last point, this is topic of this workshop, service and maintenance. That's when we need to interact with the real environment. That's where this question comes in, the perfectly synchronizing real world. In this way, so my point is even 3 out of 4 application of digital twins, we don't need to have a perfect synchronization of hardware and software, okay? Only just a validation in the beginning, then it validates the simulation. The even last one is the difficult one, and making it perfect takes an infinite amount of time. You need a better sensor, better actuator, but also this virtual fixture, or this thing can, if you provide good amount of damping in the virtual fixtures geometry, we can stabilize it. It's similar to having this passivity control in remote operation. So that's kind of our answer.
Thank you. I'd like to ask Luca. So you showed some very impressive experimental results, and you've got your digital model. So what's your view on that that need to do that experimental validation of the digital worlds?
Yeah, so that kind of validation is what we do typically to benchmark the algorithms we design, and it's definitely needed. I would say that we have 2 ways. I was presenting 2 ways to do that, or at least 2 ways to benchmark algorithms to build digital twins. The first one is a bit strange. I was actually using simulation, photorealistic simulation. I was building digital twins of the digital twin. So I was building digital twin of a simulation. And in that setup, actually, it's a setup that for prototyping algorithms makes a lot of sense. You have ground truth of everything. You can really validate. The reconstruction that you make with your algorithms, and you can also push for very challenging environments. So it's something that actually I think it's a great starting point for validation. Also because this a lot of the algorithm we propose really they do not use the information that we are using input data from a simulator. They just use camera images and they just process that. At the same time, there is the need to benchmark and validate on real data, and that's difficult. The typical way we do that on our side is to there are 2 components to it, I would say. First of all, there is the trajectory reconstruction that we make for the robot. And that's pretty easy to evaluate. You can put a total station, you can put a Vicon system for which you have a ground truth to benchmark against. So that's the easy part. To benchmark the 3D reconstruction of the semantics, it's very challenging, actually. For the 3D reconstruction, typically what you do is to use much more accurate sensors. Instead of if I want to benchmark a vision-based system, I can put LiDARs, and that's exactly what is provided, for example, in the Europe dataset. There is a very accurate 3D reconstruction of the room that you can benchmark against, that you can compare against. But then it gets even more difficult if you think about semantics. To validate the semantics, you must have a human in the loop who is essentially looking at the 3D reconstruction and judging if the semantic reconstruction is correct or not. So we do a lot of that, but the way to validate and benchmark this kind of 3D reconstruction approaches is not as easy, I would say. And actually, I'm going to give a talk in a couple of hours at a different workshop on benchmarking and validation for robotics.
Brilliant, thank you very much. And we're coming to the end of the Q&A session. We've not been able to answer all of the questions, and there's some interesting ones that have just come in, and I'd encourage you to ask those within the breakout sessions for the mind map development. But I'd just like to get the panel's view with one last more generic question. Is the phrase digital twin the correct phrase to be using? Because actually what we're talking about is something more like a cyber physical system, or it's like that David mentioned at the start, or Young Park mentioned mixed reality worlds. And actually digital twin, does that give the wrong impression that it is a digital only activity, when actually it's more digital and physical working in harmony? You can't, clue is in the word twin, and we seem to ignore one half of that. So just kind of, I'll ask each member in turn, a quick, 30 seconds. What do you think this should actually be called? So we'll start with David. You happen to be top left on my Zoom screen.
Thanks, Simon. So yes and no is the answer. That's a good academic answer, isn't it? Yes and no. You're absolutely right about digital twin. It's confusing. There's a big community of practice who don't always think about digital twins as being what I think of them as, which is this thing that's synchronized with the real assets, the synthetic environment. Maybe a little bit like Luca was using for his offline validation of algorithms. That's why we use digital twin to engage that community, so they sort of wake up and pay attention. But actually, it's the wrong language, and we wrestled long and hard with words. That's always the hard bit. Cyber physical fabric was the phrase that, for us, said it. However, it needs to be adopted. Otherwise, it doesn't mean anything to anybody. So I'm in the market for new phrases.
Joaquin?
I don't have any particular view on the name. It's difficult because, as commented, for several people means different things. So it is a challenging term that maybe actually there is no one single term to describe everything. So for example, in the chat, they were asking how fast you will update your twin, and then maybe there is a little bit more of estimation in some cases, and a digital twin like you keep in simulation running is difficult, and I don't have any good alternative to how to describe several things at the same time. But sometimes we enjoy these kind of terms just for sexy proposal titles.
That's a good point. Young Park, you use the term mixed reality, I think.
Yeah, I think we came from different places. Was thinking the same thing. Try to think about like a digital and physical twin. That's exactly what I thought too. But thing is, digital twin seems to have a broader meaning than just the physical interactions that we robotists think. Digital twin, in addition to physical interactions, it also has a data analytics and machine learning, and those are parts. So it becomes more intelligent, more on the brain too. So I don't know. I haven't come up with a magical word, but it's good to have an all-inclusive without being a too long name. I don't have solution.
Yeah. No, so it's one of those. I've just thrown you on the spot. I realize this is your worst nightmare question at the end of a panel session, but we go into this with the knowledge that there isn't the correct terminology, but actually it's part of the debate. It's part of the discussion. If we're going to shape this this area, if we want to lead it, do we need to adopt new languages? So I'm going to ask Manuel from an HRI perspective. Is there, do you see this language issue, and is there something or terms that need to be thrown into the pot?
It's not even an HRI issue. Terms are always an issue, right? So everyone understands something different. So I mean, I would say a digital twin is a virtual representation of a system. I don't want to say technical system, because humans might also be in this system with live updates. So why don't we call it a live updated virtual representation, system representation, instead of a digital twin? Yeah,
that's a very good point. Sogmoon and Luca, you're unfortunately at the end of this. Do you have anything else you'd like to add to that?
Yeah, for me, digital twin and cyber physical system are very confusing concepts still. So every time I look up the internet and definition of the terms, everybody says different definitions. So, well, I would say digital asset would be another alternative for digital twin. Yeah.
Luca?
I think, well, first of all, let me say, as somebody working at the intersection of multiple communities, like robotics, computer vision, I'm quite used to this kind of issue of like similar things being called in different communities with different names, and the naming in general being a problem. I definitely see that the term digital twin is a cool one, but is not really stressing. I think that's what David was also mentioning. It's not really stressing the dynamic nature and the kind of synchronization that that you must have with reality to keep this representation up to date. I think Facebook was also was calling this kind of maps. Also was talking about live maps actually at some point to express that they're capturing dynamic elements and they're built somehow from data. I also like the idea of somehow connecting with cyber physical systems. In the US, the control theory community and the robotics community have a long history under the name of cyber physical system, which is really stressing the software component of things as well as the physical component of things. So I guess I'm telling you guys that I'm liking all these inputs. I think we should stress more the dynamic syncing with reality, dynamic connection with reality. But I do not have a better option than that. We can propose the Facebook one with live maps, but that's pretty much it.
Brilliant. Thank you very much. So I'd just like to thank all of the panelists again for their excellent presentations today and for answering the questions. I appreciate not all of the questions have been answered. Please feel free to do the direct messaging if there's specific questions. I'm sure they'll be happy to answer as they progress on. This next section, we've got 1 more hour before the workshop finishes. So what we'd like to do now is continue some of these discussions, but in breakout sessions. So I'm going to open up 3 breakout rooms. One is called physical twins, one is called digital twins, and one is called digital tissue. And we've just had that discussion as to are those the correct names, but we can get the sense from those. So physical robots, your simulation environments, your digital environments, and then that cyber physical fabric, that digital tissue. And within these, we're going to discuss what are the challenges. What we have now, we've got a lot of capabilities that are somewhat disconnected. We're at the start of this journey as to where we want to be. We know where we want to get. We want this connective digital and physical world that allows us to teleoperate robots across the world, real-time updates, all of those technologies and capabilities. So how do we get from there to here? I will be facilitating the physical twin discussions. David Lane will be facilitating the digital tissue, and Manuel Giuliani will be facilitating the digital twin discussion. So I'll open those up. We'll have about 25 minutes to 30 minutes to have some of these discussions, these debates. Those sessions won't be recorded. I'll then bring everybody back and we'll have a kind of wrap-up discussion. What are the points that have been raised and mentioned in each of these sessions, and then we'll wrap up for the day. So the rooms are now open. Feel free to jump into whichever room you want, jump between rooms if you wish. I will pause the recording and I will see everybody back here in about 25 to 30 minutes. Okay? Right, I think that is everybody back in the room. Just let me check that the rooms are all shut and gone. Right, there we go. So thank you very much for staying and being part of these discussions and debates. What we'll do now in the last kind of 25 minutes is just go around the different groups. See what the discussion points were. I think we'll find there's some really interesting overlaps between them and points raised. And afterwards, what I'll be doing is collating the discussion points from each of those, pulling together a combined mind map and some output that we'll put onto the workshop website for people to use and have a look at. As I said at the beginning of the session, we are proposing a special issue on this topic in the journal Frontiers in Robotics and AI. And we're looking for all kind of publications, applications for that in review papers, actual articles, and possibly kind of the position paper work. I think there's an interesting paper on just the language, as we discussed. You know, what is the terminology, because it means so many things to so many different people. Just trying to define what that terminology and language is. Standardization of terminology, I think, is something of interest. So I'll start with the physical twins, then we'll move on to the digital twins, and finally come to the digital tissue. So in our discussion group, we talked about the challenges of real world validation. One of those one of the last discussion points, that need for physical validation. I'll just share my screen with where we got to. So you know, we discussed you've got the actual asset, and again, it's the terminology. So is it a twin? Do you have local physical twins? I think this was mentioned by one of the presenters, where you've got a digital representation. I think it was Luca, a digital representation of a digital environment. Do you have a physical interpretation, representation of the physical environment? Do you have local physical and digital twins of the physical asset or the digital asset? But real world testing is really important. That validation is important for industry adoption, and the research environment is moving more from here's an interesting idea, let's see where we'll run with it, to a more impact driven, end user driven world, where we want to solve the real problems, and therefore that research pipeline, that innovation pipeline, has to go from research through to industry and commercialization, and therefore industry need to be involved at a much earlier stage. But the biggest challenge was testing in real world representative environments. We've all been there, where you've got a test in a lab and then you put it into the real world and it doesn't work. You know, new things crop up. So is there a halfway house? Is there a set of test platforms, test areas, facilities that academia can test their platforms on, their physical twins on, and industry come and look at it and go, well, that is genuinely representative. I now have confidence that I could take this onto my live asset in a way that I wouldn't if you just shown this to me in a lab. So we asked, you know, when should industry get involved? Who should be funding some of these halfway house systems? You know, it's going to be a partnership between academia and industry. Should industry be defining the simulation environments, those digital twins as well, so that they become more representative? We had a discussion about cybersecurity from a physical implementation, so that physical asset, the communication systems. Are we interested, or are we concerned about industrial espionage, hijacking of the robots? Chris Kidd made an interesting point about GDPR. The data that you're capturing, if it involves personal data or people's faces, that has GDPR implications. And what happens to the operational teams of the existing assets? So you might have a ratio of 5 operators to one physical robot. How do we flip that so that it's one operator, 5, 10, 50 robots? And do we need to define new jobs and job specs for that? And finally, the data requirements. So physical assets, physical twins are going to generate a huge amount of data. How much of that is dealt with on board the robot? How much that is periodically sent back? How much of that has to be sent back in real time? Because there are always going to be latency and bandwidth issues, and we want to add more robots. So is that going to compound that challenge and that issue? The answer isn't throwing more sensors at the job, it's using smarter sensors. So how do we stop the robots from just overloading the operators with too much data? So I will, those are the points that were raised in the physical twin. Manuel, do you want to share what you discussed in the digital twin?
Yeah. So we completely ignored the mind map. Sorry about that.
Okay.
So we discussed. Well, I mean, we started a discussion a little bit with. So we talked about that actually having VR glasses and cheap VR glasses available now is actually a really nice way of making use of digital twins and simulations and connecting to each other more. So there was a little bit of discussion about this, you know, available technology now that makes it easy for everyone to connect. So we, I think we had the similar discussion to what you had. And this came back to the question that Chris has asked in the main panel before about so what is it that industry can do to close the gap between simulation and reality. And we asked around in our discussion group if anyone had experience of working together between industry and academia and exchanging data there, and there was none. At least in our small group there. So I think one thing that we all agreed on is that, I mean, in order to build useful digital twins, you need to have a real connection to a real world system. Otherwise, how would you know how this system works physically, for example, and so on. So maybe there's a challenge there to go into creating data sets or benchmarks or, you know, more collaboration. Yeah. Then we also discussed the need for new sensors. So that almost, you know, goes into what you also discussed, the need for new sensors to monitor your system for the digital twin. How often you would update the data in the digital twin. So, I mean, we gave the example, or we discussed the example of nuclear decommissioning, where you have someone, a human operator, going into a nuclear facility maybe every 3 months or so. So would you still call it a digital twin when you don't have actual live data there? So the question is, how do you get, for example, update sensors for live updates into a old facility? That's quite important. And then we ended the discussion with the question, what is it? What is actually a digital twin, and how is the term defined? So similar to what we also had as the final question to the panel earlier. I think Mohammed said, you know, isn't a digital twin a hardware in the loop simulation somehow? So I quite like that term. You know. But you know, directly, you know, following this actually quite nice term, hardware in the loop simulation, we had a discussion about, could that be misunderstood, because for a control engineer, in the loop means something completely different than, for example, someone like me who's coming from human robot interaction, who would say in the loop means in the system. So yeah, as you can see, it's quite complicated. But yeah, I mean, so generally, I think we agreed that a digital twin is not only a live representation of a system, it is a combination of live data plus a simulation.
Brilliant.
Yeah.
Thank you very much. Some really interesting points there. And as you said, they mirrored some of the discussions we'd had before and in the physical twin discussion group as well. David,
Hey.
How did your discussions go?
Good. I'm going to share my screen because I have a mind map. Here we go. Hey, hope you can all see that. So there were only 3 of us in my group. So Andrew Duck from Babcock and David Leal, who's part of the UK, or the National Digital Twin Programme here in the UK. So it's a very UK-centric view, I'm afraid. But we were thinking about this challenges federating digital twins, smart machines, and AI. And so we came up with 4 areas that we were thinking about infrastructure, about adoption, about standardization, and about trust. And in no particular order, I'll run around clockwise because I'm that way inclined. On the infrastructure side, we sort of got worried about contracting templates between organizations. You know, if you're going to federate digital twins across 2 organizations, what's the contract? Or do you need a contract? And certainly people get very concerned about data, the value of data, but also privacy with data. And data trusts is an area that certainly is in AI in general and in nations is something that people are thinking about hard at the moment about how to do that. So there's a big area. Cybersecurity, we've already mentioned, make sure you don't get hacked. And the havoc that can be wreaked if, bad actors get to your physical asset and mess, or indeed get to the digital asset and mess with it. So it messes with what the physical does. So there's a whole area there that you've got to be really careful about how you deal with that. And then there was the process of discovery. How do you know what digital twins are out there? And it's kind of, if you go back to the web as the analogy, in the early days of the web, there was no Google, and some of us here are old enough to remember that. And the web didn't really take off until Google worked. And you could do this process of discovery by searching. And so there's an equivalent with digital twins, which is query rather than search. And there's a subtle difference. You're asking questions of other digital twins, which then led us on to, well, what to include and what to exclude. I mean, you could make a digital twin of absolutely everything. And maybe that's what will happen in the end. But, do you have the HR system, I think was the comment, alongside some of the other processes that are involved around the digital twin? So what's on the inside and outside? So that's as far as we've got with infrastructure. On international adoption, we talked about standards and ISO standards, and that's one of the ways that adoption happens, is because ISO are leading the way. And indeed, David was pointing out that there's already some ISO standard work underway, what used to be called product data, but is now called industrial data, about trying to standardize what that is. And there's some UK efforts pushing towards that. There's a lot more in international adoption that we could have talked about how communities come together and open source and all sorts of things like that. So that's kind of wide open. And then on the standardization itself, we talked about how do you standardize the interface between different digital twins from different vendors, and indeed from different kinds of environments. They're working at different scales in space and time, actually. So how do you rationalize all that? We talked a little bit about what are the sort of KPIs and metrics we would use that measure the performance of the digital twin or the federated digital twin. And actually the KPIs that people are interested in depends very much on the application. So there's a bit of thought around that. What does success look like? And success is something you do want to report either to your management, your shareholders, your customers, your stakeholders in the broadest sense. And then we talked about terminology, and others have talked about that. What do we call things? The common language that everybody uses. And if we refer to something in the digital twin, are we referring to the physical thing? Be careful how I say this. If it's a pump, I think this was the example, I think David said, are we talking about the actual pump itself made by the manufacturer with the serial number, whatever it is, or are we talking about the function that a pump carries out? And there's a huge issue there, because the actual pump doing the work could have been changed out overnight by the maintenance team, which makes a difference to how your twin continues to operate. And then finally, in standardization, there's terminology about how we talk about things and how we think about things, but there's also ontology, which is the language that digital twins use to talk to each other. So it's the semantics of what is an entity and what's its relationship to other entities in the world. And the argument is that you would want to have an ontology that's as standard as it can be, so that you can take any digital twin and translate it into a standard ontology, which enables the interface between twins at the top. So there's a whole lot of work going on that. And then finally, trust. And that's a big topic in its own right. Who owns the data? When all this exchanging is going on, is it the digital twin provider, or is it the person who owns the object? And when you exchange data, who owns it? So that kind of links back to the data trusts and the contracting piece. There's some discussion about privacy and things like privacy in the supply chain. If you've got a tier, you know, a tier one, let's say, subcontractor with lots of, sorry, a tier one contractor with lots of other subcontractors underneath, they may want to maintain privacy of their supply chain. They may not want that to be public, but they may also want to be able to share data from the supply chain to other digital twins. So how do you build in that sort of privacy element so that you only communicate the information that is appropriate? And then the other part of trust is, do you trust the performance of the other DT? Does it meet spec, the digital twin? You know, does it do what it says it's supposed to do within the time constraints? For example, if you're trying to be synchronous in real time, and indeed, do you trust the operators of the other twin? Are you confident in their intentions? And indeed, are they benevolent? I'm old enough to remember the benevolent agent assumption in distributed AI, which came about in the late 80s, I think, when people started talking about that. So there's a whole lot of things there you have to think about. And most of us, as certainly in my echo chamber, are liberal, well-meaning individuals who believe in the good of everybody. But you know what? The whole world isn't like that, right? And so therefore, how do you build in the checks and balances to deal with, you know, actors out there who don't have your best intentions or don't have the best intentions of the community at mind? So that was pretty good for 15, 20 minutes. It was a great discussion, and I'd like to thank Andrew and David for the conversation that we had. Thank you. And indeed to add anything that I've missed. Thank you.
No, thank you very much, David. Very comprehensive and sounds like some really interesting discussions. We've got a couple of minutes left. Does anybody have anything they'd like to just finally raise or ask of the panel, or any parting kind of views that haven't been mentioned or raised just yet? Feel free to either raise your hand, or I'll give you 30 seconds to type something in the chat, even if it is yes, please wait. I think the discussions we've had so far, you know, there's been a lot of overlap in those breakout groups. I think that there's commonality. I also think there's a lot of it's a lot around the language. I'm just trying to, sorry, it may be a Monday, but it's a bank holiday Monday in the UK. There's a lot of misinterpretation and a lot of different people interpret digital twins, digital assets, physical twins in a lot of different ways, as we've discussed a couple of times already. And it's going to be interesting how the community moves forward in this, in reaching some type of consensus, or what the end language is going to be, or whether we stick with what we have, meaning, you know, one thing meaning several different things to different people, but it's all contextual based. Okay, nobody's raised their hand or typed anything into chat. So what I'd like to suggest is we'll end the workshop there. I'd like to thank all of the presenters for some absolutely fantastic presentations this morning, to Manuel and to David for leading the breakout sessions. Thank you very much for that. I hope everybody has had a really interesting morning, afternoon, or night, because I appreciate that everybody is in different places of the world. Especially thank Young Park, who it was 3 o'clock in the morning when he joined initially. So I think it's breakfast time now for him. What we're going to do now, this hopefully will have been recorded to the cloud, and I will be uploading this to YouTube over the next week. I'll be talking to Manuel and David, getting their inputs from the breakout sessions, providing a combined output that we'll put onto the breakout session. Hopefully we might consider running a similar one. I think it was very popular this year. We had 80 people attending at its peak, which is great to see. So hopefully this is the start of pulling together an international community in this workspace. I think there's a lot of exciting potential in this. and I think there's a lot we can do with it. So thank you very much, and I hope you all have a good rest of the day. So thank you.
Thank you.
Thank you. Bye-bye. Thanks, Simon.
Thank you, everybody. Thank you, Simon.
Thank you very much, Simon.